just take
Okay. Okay, I'm going to start introducing the morning. So we are going to have a set of presentations of 5 students of the Sea Bioma group. Now, maybe a few words just to introduce what we have done and what it all means. I have set for the students the ambition that whatever they were going to design and build was somehow related to growth, to nature, and to the environment. There's a lot of talk about environmental issues, sustainability, lots of interest in nature and in species, but there is far less done in which you really have a hybridity between the species that are growing in particular environments and real physical matter. And so the real challenge for this group is to seriously, in a literal way, intertwine it in a physical way through prototypes. So we have discussed a lot the change from the idea of making models to doing prototypes, where things are in a one-to-one scale. They are to be understood exactly as they are. Last year, we ran very much a similar strategy, but the course was shorter. It only had 6 months, whereas this year, the students had the privilege to have 9 months. Well, at the end, the privilege was more mine than the students, I think, because it gave me the chance to supervise or give guidance to these projects for longer, have more of a time to mature the work, and I think it's visible in this exhibition. When I came in this morning, just half an hour ago, and I saw the work for the first time, I almost felt it was not the work I have supervised. It felt as if it was done by the students themselves, and it has a level of maturity and accomplishment that simply in 6 months is not possible. So I'm hugely relieved and I'm super proud that the IAC has made this change. And I think actually this course, currently as it is set up, is a bit of a role model for other schools to follow. Because there are very few schools, if none in the world, that in fact have this model, that you have a post-professional master's course that allows students to do in 2 years a project that is very much their own project, at the same time that the school gives them a lot of guidance, support, skillings, etc. So all this is in place and is starting to really play out on a very high level. What I think is the big challenge for this group of students and for the school and for myself is how this work could be applied in reality. I think the next step is to go beyond the prototype, is actually in fact to think of how to install it. And I think one step was made already, which was that a few students have worked with the industry already. So that is already an incredible achievement, that you as a student in an academic environment have the trust from the industry to go into their facilities and start building things that they in the industries believe is pretty close to what they could in fact do. And they feel the interest in what we are doing. They feel the curiosity and they see that there is a potential application. That is showing me that the next steps to follow is really to see how this work could be installed in galleries, in the public spaces, on buildings, and where the industries might want to follow it up. That is clearly a conversation for the IAC to have with the industries and to see how these collaborations could be continued. I have said it last year and I will say it again. The setup that exists currently here is so unique that the work can only come from here. And I have been running a very similar program at the Bartlett, and it just doesn't work in the same way. It's just a totally different course. The students are different, the school is different, the work ethos is different, and the work that is produced here is of a standard and of a completeness and of an integrity and a maturity that I have to admit cannot be achieved individually where I am currently at the Bartlett in the post-professional master's course. And there might be many reasons, but the reality is that this type of accomplishment that the IAC is achieving currently is really unique to this place. And I have been thinking a lot about why that happens, and I think there are a few interesting reasons. The first one is the scale of the school. I think the school has still a level of a family feeling where students can go downstairs and talk to the director or to the coordinator of the course or the person who runs the workshop without having to plan a meeting that takes place 2 or 3 weeks later. It just happens on the spot. I think the scale means also that people know each other, and when support is needed, support is there. There's a real feeling that we are here to help you to achieve something that we at the end, as the IAC, are proud of. And that's something unique. It's phenomenal. Keep it. The other thing is that there is a culture of doing. And I think students here are not afraid to do a few things that sometimes look ugly. They look shit, they look ugly, but that's okay, because in the process of being made means that at the later stage, things will look incredible. And I think, again, the exhibition today is showing that. You look at some of the work, and it's so unbelievably exquisite. You would not believe a month or 2 months ago that this could happen. But it happened because a lot of other shit stuff was done, basically. And risk-taking is something that is really difficult for institutions to embrace, because it's easy to say, oh, yes, we're very experimental. But it's very easy for people to say that, but very hard to do it in practice, because there will be all sorts of mechanisms whereby the institution is jeopardizing that by saying, no, we always have to have a very high level, or we feel embarrassed, this work doesn't look good at this stage, or this cannot be presented for some reason, or it's not well marked. Actually, the work is in progress, and sometimes it looks terrible, but it has to be done like that in order for us to understand that something else has to happen. And this risk-taking, I think, is in the heart of what the IAC does. It, in fact, takes risks, and it's super, there's an atmosphere where people are super happy to embrace newity because it's just interesting. And I don't think it's a modernist statement. I think it's actually pretty much a postmodernist statement of saying that newity can be also old, can be based in old traditions. It's just interesting because it's a contribution that the school makes to the wider community and to the wider architectural community, for sure. And then I think there's this hands-on approach, which I think is also wonderful, and that is that people do. They don't chat a lot, they do. They are not spending huge amounts of time theorizing about things. And again, I think that's a school culture. There's a real sense that, look, if you're talking about something, show me what you're doing. And if it works when what you're doing, then let's go with it. Means that in a place that doesn't have bureaucracy, where things are clear-cut in terms of support, where there's a real pleasure to go for the new and to risk something that hasn't been done before, that hands-on approach will be successful. And that's what happens. Things turn out to be great because there is all this rest of stuff in place. And then I would say the last thing is that I think there's some incredibly talented people around. I think there's phenomenally talented students. And I will say something that might sound odd, but not all the students come from the glamorous universities and schools before. And maybe that's their advantage. They don't come with the pretension that they're already sort of the grand characters. They come from wherever they're coming from. I feel super happy that I don't know where they come from. I know barely the country, but I don't know whether the university is great or shit or third rank or first rank. I have no clue. It doesn't interest me, actually. I feel incredibly liberated by the fact that they are who they are. And the students are highly talented, capable, have their antennas out and know exactly what's going on. Means that I didn't have to come to tell them that somebody was doing something elsewhere, because they knew. To a large extent, they were pretty aware. Through the lecture series, through the conversations they have, Barcelona overall, means that they are aware, they're talented, and they need the 9 months, which they have now, to digest the work in order to place it properly. And the work you're going to see has to be interpreted on various levels, because it's not only the making and the manufacturing, it's the fact that it embraces biological complexities. It embraces an environmental analysis of the specificities of the context. It looks even at cultural issues in quite a few cases. It looks in very high level depth at the material and material performativity. it looks at design. It's constantly designed. It looks at geometry. It means that these things separately are much more easy to tackle, but when you merge them together, they're incredibly difficult because they do not make sense at the beginning. They are separate conditions. So it's very easy that somebody discusses a lot the geometry in the formal aspects, but then has huge difficulties in translating it into a cultural context or talk about the environment. They are much easier dissociated aspects. Whereas bringing them together takes time for students to place themselves. And I would say, and I would argue, that the 5 students who are presenting today, all of them go wherever they go and they have a position. They have a very clear position of how do they understand where to depart from when they design something. I think they have a very, very clear attitude that they learn to have. And the attitude is not only their own, is in fact also an IAC attitude that they learned here in 2 years. So I hope you will enjoy it as much as I will, I'm sure, but it's going to be really interesting to hear the journey of these presentations. The students are pretty articulated in presenting anyway. I never had spent time discussing with them exactly how to present because every time they did it, it was pretty clear what they were doing. So that will allow us to go a bit through the curve of their exploration that was not linear at all. Sounds quite linear, as you will imagine, was not linear. There were great moments where I left back to London and the students were left without knowing what to do. And they looked at me and then we Skyped a week later or 2 weeks later, or I came back later and they said, I want to have the tutorial first. And how's it going? There was this reaction of, it's not going, or I haven't a clue what I'm doing, really. And I said, that's okay, because it's new work. You can't open the book and simply see 10 references that are going to tell you what to do. I don't know what to do either. So let's see what we can do, how we make sense out of this, and how this gradually can be conquered, how this new territory can start making sense. And once it makes sense, it will be seriously powerful. But be okay, be calm. And I think they all managed somehow to control their nerve to get through the course and to present what they're going to present today. So thanks, last word, obviously. Thank you to the team that set up this show. I mean, I heard that you 3 were sort of in the heart, Maria, Matilde, and Marco, but all, Jorge, and all the rest that came in, I feel embarrassed to come in this morning, haven't done anything, and see a finished show. Never happened to me before. It's sort of phenomenal. It's incredible. So the amount of effort that you put in, I think even throughout the whole year of giving students advice, giving me support as well when I was not around, is amazing. And the show outside the IAC sounds always sort of easy. Yeah, you just set up a show at the final presentation somewhere outside the school. Well, it's amazingly difficult just to get all the stuff out, coordinated, etc. So a big thank you to you for having made it possible. All right? Thank you.
Okay, guys, just to tell you that we have 15-20 minutes for presentations and 20 minutes for comments. Okay.
Hello, my name is Wilton, and my project is a proposal of a decentralized uh, water filtration system for Rocinha in Rio de Janeiro. So I've been always interested in making the. And I started reading about wastewater and water recycle, and reading how our sewage system, our treatment system, has been constantly evolving since the Romans, and and then you have the first revolution where the Romans managed to pipe the water through the cities, and then they start to treat the water, and now those days they have all the sewage center systems. The problem is that we waste a lot of energy collecting all the water, taking far to these places, treating there, and then bringing back. And my proposal, what I see as the future of water treatment, is to create a decentralized system where you can filter the water inside, somewhere close to it. So the upcycle concept is to reuse waste materials and get the best out of the trash, let's say. And I'm using the ceramic membranes for filtrate the water. They have been using since the 60s, and today they are mainly used in industries because they make no difference between gray water, black water, or chemicals. They just block and they filter everything. And the ceramic membranes, they use 50% less energy than the reverse osmosis ceramics membranes. The advantage of this system, the side stream membrane, the side stream is where you have the bioreactor, which collects the waste and gives the energy for the system to work. You have this bioreactor separate from the filtration system. And the advantages are that it's a very stable process, easy to maintain, if you need to make adjustments, you just remove a block because they're made of 1 by 1.5 meters, and a high effluent quality. Later in the video, you'll be able to see better. So how it works is a cross-flow system where you have the retenant, the wastewater basically going straight through these membranes, and the clean water across the walls of the membranes and comes out clean. I'm using I'm proposing aluminum membranes as for the filtration, recycled PET, which can be found easily in the area, and aluminum for the structure of the hub. And it can take pH resistance from 0 to 14, and I can filter from 170 to 298 liters per square meter per hour in these membranes. So as I input, I have a wastewater, rainwater that I'm collecting from the roofs, and inland water to prevent floating. And as output, I have the energy, potable water, and the flood prevention system. So about my site, Rocinha, it was considered the biggest slum in Brazil. Since the 1903, it was declared a neighborhood because it has almost all the infrastructure necessary to be considered a neighborhood, although it lacks a lot of infrastructure such as transportation and sewage system, garbage collection, and so goes. It's a really, really steep terrain and super occupied. today, it's the official data counts as 80,000 inhabitants, but the people who live there say it's almost 200. And my sites are the solid rocks that I can find in the terrain that were not occupied yet. And I'm placing my structure up in these rocks. I've highlighted some. And so the sanitation system in Rocinha, it's really poor, as I said. It's only 53% today, which is a proper sewage system. The others just flow down the steep and end up in the ocean eventually. And I'm making the connections to collect the water to bring to the hubs by gravity and shortest path. And I collect all the waters using the pipes that already exist there. They are all external because houses don't have this infrastructure for it. And I'm using the existing pipes to collect the water, take to the hubs. And after the filtration, the clean water goes down using the gravity, so I don't use more energy. As design inspiration, I used the water flows, this fractal system, and the chaos of the place of my site. And about evolution, I did some studies. This was my first one, using membranes. But what I wanted something more open, where I could pass the light and pass the wind, so I don't block completely the view. And then I start looking for this system where it flows down with the gravity. And on my second term, I present this tree structure, which was a fractal structure using membranes also. Now I'm using fractals, but in 90 degrees, not as I was using before. And then I start looking at this nest structure, this chaos thing, until I end up with my final model, my final hub. And I didn't do prototypes because of the complexity of the material. The aluminum is really complicated to work, and it's an industrialized process. So I made a nice video. Hope you guys enjoy explaining how it works. So first I select the houses that need this water, that don't have the proper sewage system. And then I bring them to the available spaces using the gravity, as I said. And here you can see first the membrane growing, and then the pad structure which holds the clean water. And I also have the separation made with aluminum every 1 meter, so I can manage to, if I need to substitute replace one model, I just take out another one in the place. And the bioreactor have a pre-treatment, which is a fine grinding, so I avoid fouling on the membrane. I filter all the water. The outcome goes to the bioreactor to generate the energy necessary to pump the system. And if you need it, I can run again and again this filtration until it's completely clean. The hub becomes a gathering center and a place for people to walk from the up part to the lowest part of the terrain. These are some of the hubs of the proposals. They are all made with 1,000 segments of 15 to 35 meters long each, and they are able to filtrate from 200 to 500 liters per square meter per hour. It can be adaptable according to my needs, the amount of water that I need to filtrate, and also the space that I have to build. If it's a large rock, I can make a wide hub. If not, I go vertical. And here you can see all the connections using the already existing pipes to bring into the hub, and then from the hub it goes down and keeps going down. And as the final, an amazing view of my site and the city. Thank you very much.
Thank you very much, Wilton. So we spent 13 minutes. We have 40 minutes per person.
Okay. I might just say 2 or 3 things to explain, which Wilton mentioned, which is in this process of what I call the risk-taking, experimentation, there are things that don't work. And then I think in Wilton's case, the prototyping did not happen at the end consciously, because for a long time there was the intention to physically make these pipes that exist in an industrial manner, which the industries never wanted to share with Wilton. They didn't want to even to sell one of these pipes to him. And every time Wilton tried to remake it in-house with this particular type of clay that has a particular mixture, it cracked so badly because it's it's a very difficult process to get this material working, plus full of these perforated longitudinal internal channels that are highly, I mean, they're very, very difficult basically to make because you need a proper extruder and you can't replicate it. That's the point. And this went on for so long that at some point we both sat down and I said to Wilton, there's no point to continue because you will end up at the end with a story that doesn't make sense because you didn't have time to tell it properly. You won't have prototypes because they're all broken. And you can't really finish. So the change here was to say, this is not a failure. This is where failure is part of the process. One has to accept that. I think the great advantage was that you had time to give us a film that started talking about what this architecture could be. And that meant that it was not too focused on the tube and the pipe itself, but actually the piping overall started creating an architecture. So the architecture emerges from this lack of capacity to deal with a small prototype. You will see in some other work that you might see less of where the application is. I think in this work there is more of a sense that we might want to criticize of where it's placed, what it is doing, and what the architecture is that you're proposing. But I think it was a conscious decision, and I'm glad to see that there was a film where you could see the sequence of events, and in fact, all these different options. They looked slightly similar. I was imagining that they would probably be more different, but you could perfectly feel as a designer that there was a principle that you investigated that could now be applied to different situations with very different geometries even. And that in itself is a very potentially interesting thing. It's the type of project you can go out and talk to local authorities and start talking about what this could be. And I think there is an interesting idea here.
No, go ahead. Okay, first one question. What is happening inside of the hub? Is there a program or?
No. Well, inside of the hub, it's just I have some stairs so you can go into a viewpoint, because today in Rocinha, people open their houses, on the ones on the top of the hill, so the tourists can go and contemplate the mess and the slum. And so I'm creating this kind of viewpoint and a place where people can gather and pass by, especially because it's so difficult to walk there. You have some alleys, and then I'm connecting this from the top of a street until the bottom of another one. But it's not a specific program going inside.
Okay, so in this kind of situation in which we are colleagues, basically, you are architects, we are all in talking to intelligent people. I think the best we can do is making suggestions to make this grow, because it's your career what is after. So any positive suggestion is going potentially to make you success as architect. So this is the way in which I will try to make my feedback, making suggestions on how to grow your project. So I have 3 suggestions. First of all, I think growing from the idea of recycled materials to the idea of cradle-to-cradle treatment of materiality could be quite interesting, so that not only you are using materials that potentially has been used previously, but also you think how your hubs could change, and will change for sure. I mean, I don't know if you have been in this area of Rio. I have been doing a couple of projects there, and it's super organic. It changes constantly. It grows. It decreases, and this is basically one of the advantages. People tend to think that it's better to live in formal architecture than in informal, but of course you have advantages of growing up as a children in a favela. There are no cars. You can put another room to your house if you have another brother. There is a substantial way of living that for me is based in the idea of allowing change. So I think it could be very, very interesting if not only you are thinking, where do I take this from, but what am I allowing others to do with this stuff once it's there? Are they able to change? Are they able to readapt? Are they able to grow? Are they able to make it more dense? Are they able to make part of this disappear, getting rid of things? I think this will make the system much more intelligent and adapted to the site. A certain organicity on how to allow change. For that, I would say, for example, making a non-continuous tube, like a horse, but making something, or a worm, but making something that is distinguishing between the linear elements. That, I mean, aluminium is a very difficult to assume material, but let's assume you are using aluminium. It has certain good things. Of course, you can recycle, but I only think you can recycle aluminium in the linear pieces, and people potentially could only use the linear part of your tubes in the future, because probably the radius, the curves, are the bits that need more adaptation to the places you have to. So I think adding joints to these tubes, making more intelligent what is the material that is going to apply in each place, like where the tube is starting, where it's blending, where there is a linear bit, where it's having a more structural performance, where it's just water conductor, and all this would be super interesting, like making ribs or making connectors, so that probably you have clay pieces, aluminum pieces, plastic pieces, in a kind of less continuous kind of a structure. Adding this will allow people to dismantle parts, to reassemble, to reconnect, and probably to reuse much better the linear pieces in the material that is requiring more energy in the whole world and that is not renewable. So it is very, very, I think you have to be very reflective when you are using aluminium, how you are not avoiding others to reuse your material after. So linear pieces is, for me, it will be very interesting. Then I think there should be, or there could be, a very interesting reflection on redundant structures, because structurally, at the moment, your lines are not collaborating each other to make the nest. And what would be very interesting is making it even lighter, because it works like a nest. Nest is working like a unit because it's supporting every stick in each other, so they are lying on each other and they are creating this bit. If you can think about connectors that could join together this redundant structure, you will be able to make every element lighter, because it wouldn't be like 5 meters cantilever each one, but it will be. So I think connecting the structure will be another very interesting situation. And then just very briefly, there is a very interesting comparison between informal slum urban. It's not urban design, it's urban layout, let's say, and the formal layout when they are dense. If you compare a very dense, let's say, Manhattan city that is formal, that is planned, that is planified, and the slum, they have something that is very, 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 very different. That is the occupation they make of the ground. In the formal density, you still go to ratios of 40% of the occupation of the total ground to 60. And then 40 to 60 of the total ground or the total soil is not occupied. Even if you go very, very high, as let's say top Manhattan, in which you are 200 houses per hectare, you have still a lot of vacant soil. In the slum, that's not happening. You might be in 100 houses per hectare, that is very dense, and then the amount of space that is not occupied, the amount of ground is maybe 10%, it's no more than that. That's what is very difficult, and that is what is making a lot of sense to think about how to put the urban installations as you are doing. But because of that, I would really suggest that maybe doing kind of courtyards, in which what you are doing is a hub, but is precisely an empty space in which social things, installations, future necessities of the community can be solved in that place that is precisely reserved for something, because that's precisely what the slums are not having, that is ground. So I think thinking of in your space like a courtyard is not having any function. So let's enjoy that emptiness.
In fact, the whole idea was about creating these social spots on pieces of topography where there's nothing built, because the inclination is so steep that not even in the favela of Rocinha they managed to build. Means that there was a sort of 60% inclination, nothing could happen there. And because of exactly that voidal condition, the idea was to take the opportunity to create a social hub at the same time that it's a water remediation one. And I think what is, okay, it didn't come across completely because you didn't actually show how it could be used. You showed only the principle, but you didn't show in your video the possibilities of use. But what was, I think, sort of interesting and intriguing at the same time is that the pipes become so intense that the space almost disappears in the middle. And on the one hand, you think, okay, he's so fascinated in love with his thing that he's sort of multiplying the pipes until it becomes this nest. And in fact, nests are 60% or 70% matter, and then there's a tiny bit of space which is very cozy for the birdies or whoever animal lives in it. Means that there's an enormous amount of bulk of material and very little space, and that's part of the power. And there is something about this porosity of the big chunk of tubes that create this tiny space inside. But clearly there was a sort of ambiguity where you think, is he just in love with it and indulging with it in such manner that he's becoming uncritical? Or is this an interesting strategy? I found the neons really intriguing because I sort of liked it. It was sort of a techno-social environment in the middle of a favela. And then with the music you chose, you think, this music is not at all about the social stuff, you know, all the difficulties that exist in around. It's sort of the fancy Rio guy that from the Leblon area designs this fancy hubs that do a bit of water remediation, but actually like this fancy stuff in the middle of the favela. And I think that's a criticality that you have to have. You need to be able to place yourself there. Is this appropriate? Is this what you really want it to be? Or is there a different feeling to the whole architecture that might be of a different genre? Means then the materiality, the light, the space you give, the access might change the project quite substantially, but that's a critical attitude that you might want to have when you leave from here.
Thank you, Wilson. I think that the outcome of the digital work, because it's digital, it's beautiful. And I was thinking, and that was a discussion that we had the last days during the presentation, working on informal settlements, it has its challenges. No? First of all, how do we deal in a formal way in an informal settlement? So what you're proposing in a way, it's a kind of a top-down formal way and process of proposing a new kind of infrastructure. And on the one hand, I am interested about this new kind of infrastructure that emerges and it's necessary for the place. On the other hand, I question the top-down design and the way that those would be implemented and would be eventually used. So if you take a look at the slums, it's asking very well described the dynamicism that exists there. There is almost no repetition. No, everything is unique because it's really like customized for the needs and it's really made, handmade out of the people that they are there. So I would have been more interested to see how those nests, they are being really customized on every place that you very carefully choose to place. And I would even allow the people of the neighborhood to be part of the process of the implementation. That is a way to raise awareness, but also that is a way to go with the culture of the place, of making the things and really being part of it and using it. So in that sense, I would have a variation of designs based on the context. following your principle of creating spaces, new social hubs? Are there always the same hubs? Is it always about a nest and a middle thing square to do what? I would create a variation of the program, therefore variation of the geometry, and I would really include the people in that process. I think that is mainly a bit what I was thinking. And what is the impact of that in the space? Can we have some numbers to understand what would that mean? I think that is also very important, especially since you don't have the process of prototyping to see how the bioreactor is working, or what is the necessary scale of that bioreactor. I think what it would be interesting is to take data of existing technologies and then trying to figure out what would be the impact on the space, because it could eventually be a solution of a very low cost solution. It could have a great impact on such settlements, and there it becomes a system that could be implemented like repetitively in different places.
Thank you, Wilton. It was a difficult project. I think almost a nightmare. Yes, but I think it would be nice if you keep working on this project, because projects are really sometimes are difficult because we are exploring things, and it's a very intricate project, as your mind. Very difficult project because in the past we went to inhabit places to use natural infrastructures. Like we would go to inhabit a place because there was a river passing by and there were some hills to live on top. But when we started to be a lot of people, we had to build artificial infrastructure to use more natural infrastructure. And sometimes we had to go far to bring water back into the city. I think that, as your teacher is mentioning, you would need now to speculate about a sequence of events from the past to the future, and you are the presence of these events. But I think it's almost mandatory in order to give proper answer to the questions you are putting into this project, that you understand that what you're doing is not to go and inhabit a place of a natural infrastructure. You are inhabiting a place of artificial infrastructure that you are elevated to another exponencia level, to another level. You are taking advantage of an existing plumbing system, which is very complex because probably it's not working at all. But you are basing your project not on the natural water, but on an artificial water that must be very dirty already. I think your project should be a little bit more dirty, more ruined, because I'm totally sure that the day after you build this stuff is going to disappear immediately, because these people are going to take all your aluminum and build something else in order to improve that decay that is already existing in the favela. So in general, I think when we are so afraid of, make our hands dirty, we are like the fashion designers of something. One good way is to imagine a sequence of events through these amazing tools that your generation has. Try to imagine not only a collaborative process of society, but this collaborative. What would happen in the ruin of your project, for example, because the ruin of a Roman aqueduct, as you were mentioning at the beginning, is still beautiful after 2,000 years. After 20 days, your project probably doesn't have any ruin. And I think if you go into all these questions, the problem is not like this hub for contemplation or anything like that, or probably, it's not about having this cube all over. Probably the questions are other questions that you're gonna, to bring into an industry to say, how can we develop But I think that what I really appreciate of this project is this kind of reflection that what is the future of infrastructure aqueducts in a favela. So it's like I was very fascinated by your video because I was imagining, you know, I cross my city, which is Rome, every day, and I cross through an infrastructure that is abandoned. It doesn't work anymore. I'm always thinking, how can we reuse this with young people, for example? So what is missing in your bin system and artery system, probably it's something that is existing. And I'm insisting, you know, we are here telling you what it's missing, what is good. But I think that the most difficult when we are students, how do we put questions to a project? And I think that it's mandatory that you take, before leaving for the holidays, you pack your project, imagine the past of your project, the present time of your project, and the future. Because your project probably exists only 1 week, which is good. Probably your project will feed not a contemplative hub, but another favela. And I think your project smells a lot. It's very dirty. I think it's full of trash, and it's too much. I see all the problems, and that's why I was opening my comments, say, what a nightmare. But if you bring some time in the present time through past and future, I think you can really understand your project, which is, I'm insisting, incredible forward thinking. What's the future of infrastructure as aqueducts? And what's the project if instead of, you know, there is a city, we go and take the water, we cross the land through something, and the people start to attach because they want to drink. In your process, no, you are densifying something that is already dense. So it's so interesting. But be aware, because I think it's a very successful project, but it needs better questions to be put.
Something to this. What makes me interested in it is the idea that this is a seed for something. I think there is clearly a potential conversation one can have where this is the departure point for a project, and in fact could be more real. And I think the point you're making about the infrastructure as a basic system that then develops something else that comes with it, you know, the idea of, in a way, any settlement comes when the first infrastructure is laid out or even found, is really interesting. And that clearly is there. What I found really, really incredible is that for a long time this project was about a clay-based material tubular system, and it turned into this aluminium thing. Now, I know that there are two types. There's the aluminium piping and there's the clay one. But it just shows me again of how critical materiality is in projects nowadays. Has always been, but nowadays even more. This whole animation would have changed radically its character if it would have remained as a clay-based material constructions. I mean, is that all this neon shininess that you have here wouldn't exist. It would, in fact, be a matte, brownish or grayish type of system where the hapticity would be totally different. And I think that should make you think, which is that if you change your materiality back to where it was, the possibility that even the locals are part of the crafting process of using the clay, not the aluminium, but the clay-made components. And there was for a long period of time also conversation that rather than tubes, there could be wall components, where rather than only a single element, the section is a much more continuous one. But this could be locally crafted. That would be a change. And maybe there are local industries that you don't know about that could be part of such a process of making. So I think there were some very valid, interesting comments. But altogether, I think there's a message that you should take it further. You should not see it as an end finished project. There's something about the seed for something that could come, and make the most out of it. get out to the local authorities, to these associations, to the industries that exist, that you might want to talk to and say, I have had this idea. Do you think we could take this further and actually make it happen? And if there's one prototype pilot scheme somewhere, it could then be replicated elsewhere. And because there's so many favelas and there's so many problems with water, there might be lots of people who want to listen and actually invest more time in this. Right. Good, thanks so much. All right.
So, yeah, you've noticed, no? So, okay, we have several different people, since the presentation of today include the presentation of the second-year masters of Marcos, but as well the Digital Matter studio. In the afternoon, we have different people around. I will just start from here. Izaskun Chinchilla. She's from Madrid, an architect. Izaskun Chinchilla, founder of Izaskun Chinchilla Architect. She's also a professor at the Bartlett. Then Elena Rocci. Elena Rocci, she's an Italian, but she was living many years in Barcelona, architect. Now she's in between US and Barcelona. She's also teaching at Alessin, but also at the Herberger Design Institute of Design and Arts. We have back there Manuel Kretzer. He's the founder of Materiality Research Network. We have Jonathan Mincin. He's the EAC Green Fab Lab coordinator. I don't know if I am missing some, and of course we have all the great EAC people and staff, and we will have some more jury entering during the day. So thank you for being here with us, and your feedback is valuable. Okay.
Hello? Yes, I think I'll present first and then we can have a look there. Yeah. Okay, hello. My name is Kunalji Chadda. I'm from India. And the name of my research is In Sand Out. It's about reintroducing sand to architecture. So the research aims at digital manufacturing of local and natural material for biomass production and water harvesting, using industrial waste as binders to surrogate natural resources with higher durability, strength, and hydrophobicity. By handling robotic and digital manufacturing, it's an attempt to make the construction system automated. Considering the cities of the future are living, and it's essential to consider microorganisms and a shift from the inert materials to bioreceptive materials is the key. So the objectives of the research are based on 4 main criteria. There are sand, which would be my primary material, then a natural binder, which would display the property of hydrophobicity, then the composite would be bioreceptive, and the fabrication technique. Now, why sand? Because sand covers, as you can see in the map, the deserts cover 33% of the land mass on Earth. And the problem generally is not in the desert, it's on the edges that is widely spreading. And I started looking at projects done in EAC and away from EAC on sand additive manufacturing. And the project of stone spray, they used natural material as the primary material and a glue as the binder. And in the solar sinter project, they used focal lenses to use sun and melt down sand to print. So by the reference of these two, it was pretty clear that I wanted to use natural material and a natural binder to make my composite. On this, I based my research criteria on three levels: that the composite should be of a primary natural material and a natural binder, which would display higher durability, hydrophobicity, and bioreceptivity. And using digital manufacturing and additive manufacturing to speed in the process of rapid prototyping. Now, what is sulfur? Sulfur is a non-metallic element which is placed on number 16th on the periodic table. It's strongly acidic. It's orthombic in its structure. It's available in physical state on 20 degrees. And the compound that I would be using is between sand and sulfur. It all started with the small clip, which is in this they are making the compression test for concrete cylinders, and they are making the capping with a sulfur compound. There is a company called Einor. They certify this product. So I got in touch with them, and they sent me the recipe of how to use it. So I make it sure that everything was under a controlled environment. Yes. So after looking at this video, it was clear that it dries faster, it works better in compression, and so I started working further on my research. I would just pass these models on. This composite is with sand and sulfur, and the other one is with resin, so you just get an idea of how strong it is. You can stand on it actually. Yeah. So after making the composite, I started testing it with the ultimate tensile strength with a 3-point UTS with 2 points of support and 1 point of load. And based on the formula, it gave us the results as accordingly. Like for example, just to give you a comparative strength test, brick is 2.7 Newton per millimeter square, and Portland cement is 3.4, and the material, which is in sand out, is 4.2 Newton per millimeter square. So I started looking at more. The property that was a positive and the negative in this was it was really drying within seconds. It was difficult to control it, but so I started experimenting with different materials. So I started adding magnesium sulfate and alcohol to make it more viscous, so it could be easily controlled and to lengthen the process of curation. Then I started casting them from the micro scale of casting to a meso scale, so I can see what definition of what's the definition that I can achieve with this material. As you can see, that the geometric structures are not well defined, and it was more about the curvilinear structures. Moving on from this, like scaling it a bit, I also wanted to check what thickness would be appropriate. And the reason for doing all of these and the curvilinear structure was to channel the water. I guess, yeah. To channel the water accordingly and have collection tanks which could collect the water. So these panels are water harvesting panels. Okay, the step further from this, I achieved the strength, I achieved the hydrophobicity that we were looking at the beginning. So we started looking at the biological aspect after this. There is a red algae called Galderia sulfurea. It's an extremophile, spherical and spore form red algae. It's highly acidic in nature, and it only thrives in pH levels from 2.4 or beneath. In this case, it dies when it thrives on materials which are above 2.4 pH level. So they are not harmful when they come in contact with other materials. So the chance of growing rapidly or uncontrolled is rejected. So what are the conditions that is required on this? Since I'm using a sulfur composite, sulfur thrives between 0 to 1 pH level. So it's exactly apt for this red algae. It needs a room temperature or a temperature around 20 to 54 degrees. It can thrive between them. It needs indirect sunlight. It could also thrive in direct sunlight, but indirect sunlight fastens or speedens the growth process. And the pH level, the apt pH level is 2.4, but it could vary from by 1 pH level plus or minus. But where could we apply these sulfur and sand? So this is a map where all the sulfur is produced. It's basically all the activities with combustion or even transportation. So these are the places where the sulfur is produced, which is more or less all over the world. But it's been harvested or it's been extracted close to the coastlines where they have oil refineries, which is a waste product. So you have the sand and you have the sulfur as a waste product. So we're using an industrial waste product to construct, which can surrogate a natural resource. Now, just to give you an idea of the growth rate, if put in a 6 ml container, these are numbers from New Mexico City State University. It grows by 0.1 to 1.2 grams per liter per day, with 40 degrees Celsius and pH level of 2.4. Considering that state, if you consider the area of Poblenou, we could have 13,000 liters of gas per day, which this is just to give a scale of the growth rate. Sorry?
So for like it would be enough for all the population in Poblenou or this quantity of gas?
Per day, yes. Monthly, but I'm skipping the numbers now. I mean, I'm missing the numbers, in fact. But
Enough for 10 people, 100 people, 1,000 people?
I think I mean, I don't have right numbers to justify it right now, so I wouldn't go in that. Yes, it's produced. Yeah, it's the way how you extract. It's called hydrothermal processing. It's the process how you extract biogas, which can be used as biofuel. So starting with the geometries, I started looking at the design conditions which the red algae needed. So it needs ventilation and it needs light. So in the ventilation, rather than having a solid geometry, it was important to make it more porous so it could have a nicely ventilated area. The light conditions are, since the favorable conditions are the north, which is the indirect sunlight, we could have a circular geometry at the base, or if we need to cut the southern light, we could have had a triangle. So based on this, I developed a small interface. Sorry, one second. I think I'm missing a slide. Okay. So based on this, I went ahead with the 360-degree exposure. So I went with the circular geometry as the base. This is the evolution of the geometry that I was working with. So if stacked, they would perform in different ways in plan. So they could have a variety of conditions inside one column. Okay. So the interface that we spoke about is like it's you can select the shape from here. On that, you can develop you can also select the condition that you need. If you need the growth to happen from the core to the surface, you need it with coiling, or you need it with surface to the core, and then you can extrude the geometry. I mean, you can see this interacts with this one, so you can have a clear idea of how it's growing. Similarly, it could work with different shapes and different conditions. Now coming to the fabrication part of it, for getting geometries like this, it was essential that I used additive manufacturing, and for that, we use robotic fabrication. We use an extruder of 1 liter of quantity with a length to heat it up because we needed a temperature of 125 degrees. So we coiled it with a nichrome wire of 10 meters, and the whole circuit needed a power of 768 watts. So the problem that I was facing in this was because the material was drying faster, so I had to maintain the same amount of temperature in the cooking pot and the extruder. Since the material was in a liquid state, but it dries faster, I was having problems with spilling at the beginning, but gradually we controlled it, and then we started working on the geometries which were designed. I have a small video to show the fabrication process. I'll just go ahead. When the extruder is completely filled, we get curled extrusions. And since it dries faster, so the next layer we don't need to print it on the surface of the layer. As you can see, it dries faster, so they merge together. The prototype includes the hydrophobicity, which was the main idea behind it. And these are the custom pieces which show how we are channeling the water in the panels. I would invite you to have a look at the prototypes back there.
Working. Oh, it is now. Could you quickly explain what the logic of the brick was? In a way, this thinking process that there is a small component that can be repeated, is that still part of the process? Because you didn't talk about it, even though you spent at least a third of the year discussing it. The second thing was that you showed a statistic that nobody understood, which was something about the gas production in Barcelona. And Alex was asking sort of, what is it? How does it compare? Is it the gas production of the algae? Is it the sulfur content in the air that you produce when you use this? What is it? And the third thing is what we're looking at here, if they're prototypes, are what? Are they a section through a column? Are they a brick? Are they a set of different components create a wall? What is it what we're looking at?
Thank you. Okay, so the idea initially started with reinventing the sand brick, where the usage of the conventional material is clay, which uses up a lot of land cover, agricultural land cover. So that could be replaced by an industrial waste, which is sulfur. So that's how we started working with sand and sulfur as a composite. The idea was to have a brick, so it could be a repetitive component or mass produced, so you could have interlockings and which were those ones, yes. Sorry, and then we moved on to the to the column, because the main function of the column is to bear load, and the structure, I mean the composite displays strength. So I thought it was essential that we go on to a prototype which shows the property of the element. So we went on to the idea of the column, which could also harvest or channel water, and we could have collection points. So this, what you see, is the external condition of the column, and this is the section of it in a much lower way. If you see the 3D prints, these are the sections. This is the whole column, and the idea was to have, yes, yes, yes. This is just to give an idea of where we are at the production level. Yes, so this was to show the outer condition, how it works and how it collects water, and this is how it works. Yep.
Sorry. I'm just wondering, to build up the scale 1 version of this column, will you be using this robot system you are using in here?
Eventually, yes.
So this is real scale?
Yes, this is real scale. All the prototypes are one.
No, these ones?
No, these are,
okay. These are not prototypes, okay.
These are panels which are water harvesting. Like they could harvest water, and you can channel it to specific points.
So Kunal, what is your ultimate goal? Is it to create a new composite material that could be hydrophobic, using natural material, channeling the water? And what about the bioreceptivity that you were talking about?
Yeah.
What is the ultimate goal on that, or what is the contribution?
The ultimate goal was to have a composite which is hydrophobic, so it could be hydrophobic and we harvest water. But eventually, with more research, we found out that it could also be bioreceptive, and we have growth on it, which could serve as something more than just a stagnant element. It could actually be evolved.
And may I ask, how do your patterns emerge? I mean, are they related with this performance of bioreceptivity, or are they related with the fabrication limitations, or is it related with the viscosity of the material? I mean, how do you decide this kind of channeling and this kind of formation?
Like I started working on making a small test on the surface of the sulfur, so I know what conditions are favorable for the red algae, and based on that, we started developing design conditions, and then we started working on the growth systems on it. So these are, yeah, sorry.
I might need to explain something, which is that in order to create bioreceptivity or conditions of bioreceptivity, one of the key aspects is that you have the right pH level for the species that are growing, but also the right porosity for the absorption of water. The problem with bioreceptive materials, and due to their porosity, is that they're structurally incapable of working. So they can only become cladding materials. What is really innovative about this is that this material is structurally very capable. It's amazingly powerful. It's actually more powerful, more capable structurally than normal Portland concrete, because the sulfur content as the binder, and that was the big question mark throughout the project. What is the binder for the sand? Because the binder was initially salt last year, but if it gets a bit of water, it dissipates and melts. Therefore, the whole conversation about binder is what you have constantly, for not only computationally in terms of what you're manufacturing, but for bioreceptivity. So the binder makes it hydrophobic. But the complexity of the geometry and what is called the surface roughness of the material is what makes it bioreceptive. Because this algae will never grow inside of the material. It will grow on the surface, but in the depth of the surface. In this roughness that exists here, which when you look at the through the microscope, is hugely three-dimensional. Plus, this type of maximization of surface where if you would calculate how big the surface is here, is enormous, means that you have a huge amount of algae growing here, rather than if it would be only growing on this outline. So there is an idea of surface roughness and surface morphology being highly complex in order to be bioreceptor for algae growth. At the same time, the material being structurally capable through the waste product of sulfur. What are those?
Sorry, I think I just rushed through the whole presentation with the 20-minute barrier. These cars, I was testing like what is the definition I could get with this kind of material, because in the beginning I was getting the finish with a sheen, with a kind of a shine, so which is not actually the texture of the material. So this was to test what kind of definition, what kind of linearity or geometric shapes could I achieve. As well, I was trying with different composites. I was trying to add magnesium sulfate and alcohol to make it more viscous, so I could control it for casting. So it gives me more time to handle it. At the moment, it still dries very fast. So it's good for additive manufacturing, but for casting, a bit tricky. It's still a bit tricky.
There's two really interesting aspects of this. One is that from a material point of view, you're dealing with a composite that we're not used to. As far as I know, I haven't heard any architect dealing with a sulfur-based concrete. You mentioned the company that is trying to use it, but probably the limitations of using it on site means that it can only be used in precast components that are done in a controlled environment. You cannot simply use robots on a construction site that have to be on a high temperature, that dry so quickly, etc. So the curing process is so quick. It's actually not about drying, it's about the curing process. The curing process is so quick and so fast, which is a great advantage, but also due to the high level of temperature that you have to have, that it has to be done in a controlled environment. But the fact that you are dealing with it came out of the same problem that Wilton had, the previous project, which is there was a moment where this project could not go on because the binder was not found. What was the binder for sand? Fortunately, you found something. It means that after lots of research, you found that sulfur was really this niche product because it's not the one that is produced on purpose for this. This is the waste product that not necessarily produces all these sulfur toxic gases. Therefore, you're also capable of using it in a safe environment at school. I think the second aspect, which I found even more fascinating, is that this forced you to look at species that we don't have around here. Now, rather than being harmful, what is really interesting is about getting species that can only survive in very particular environments. Means this high level of acidity we don't have in our environment here. Now, question, why do you bring them in? Well, this is an experimental project. The algae is not going to solve the world. But the fact that you're not introducing a harmful algae that could spread and take over because it lives in a very similar condition as ours, and that's usually the problem with the import of species that are not native, is that if they feel comfortable, then they take over. This one will never feel comfortable. It can only thrive in this high level acidity. So it forced you to look for extreme environments. And as you might have heard of bioconcrete, when Jan Honkers in Delft started working on what he called bioconcrete, he looked at extremophiles, which is bacteria that lives in very extreme environments that are similar to what concrete is. And it's exactly the same process. It's looking at parts of our world that are completely unexplored architecturally from an engineering point of view, where species have had the capacity to adapt to extremely difficult conditions that nature has created. And this is now starting to bring back new thoughts on how we might be using it. And I think that's where that model looks very small, but is hugely interesting, because this tube is coming actually from the laboratory through all the difficulties, even of something you didn't explain, which was to even bring it into Spain. Meant the controls of the customs took so long that the first bunch that you got died. means the bureaucracy killed the bacteria, killed the algae. And then the second bunch was sort of brought in, and a big request was made, can you please allow it to come in, it's safe, because if you take too long, it's going to die. And then it was brought in, and then you could use it. And it's totally done with Nuria, who helped you sort of manage this, because it's type of work that an architect cannot do alone. It needs a specialized biologist who is in synthetic biology. It's not even a normal biologist. It's a biologist in synthetic biology who is able to deal with the extremism that is necessary in terms of the environment for these species. So on these two fronts, I feel hugely excited about this work because it's stepping into new territory. We don't exactly know how to evaluate it. Plus, you used Houdini, which is software that very few people use, in order to start animating some of these complex geometries that you're generating.
So, I mean, you said earlier the next step would be to get this kind of research into the industry, into the actual real world. And that, I mean, you did an amazing amount of experimentation diverging into all these different directions, which is something that's, as you said, unique about this place. But what would you focus on if you were to do a PhD, or if you were to start your own business? Would you focus on the material experimentation, on the biological aspect, on the form finding, the structural analysis, the robotic fabrication? What is that you think is has the most potential in this kind of work?
I think fabrication can come into the industry much faster than biological aspect, but for sure that we don't have it.
So it would be the robotic extruder with the material. Okay.
For me, it's actually not so. I mean, I do appreciate, of course, the fabrication process, but what I see as a kind of big potential here is our contribution as designers into that. So I am really intrigued when I see this kind of different kind of patterns, and that's why I was asking you why those patterns, like trying to understand which are the parameters that could allow us to come up with a series of designs that would give performance to what we want to propose. No, so it's different if it is a column. The geometry, the inner geometry of a column would have been probably different from the formation of a cladding or of a surface, no? And it could have been much different if we take advantage of the mechanical properties or the structural properties of that material in order to create something more three-dimensional as a structure by itself. So I really appreciate the work and in terms of material experimentation and fabrication experimentation. And I think that the next step is to work on this kind of design possibilities related with the performance possibilities. And you also need a case study, exactly because this kind of biological organisms, they are not like, as Marcos was saying, they cannot survive everywhere. But the fact that, for example, algae can be in can be in humid environments, it can be in shadowed environments. I mean, all these kind of inputs, they can also help you to specify more the work in terms of context. But I see great potentiality on taking this further as a design tool and even as a kind of a new structural, let's say, propositions.
What Kunal was hoping was that he was being able to do it with that level of detail and even more. The problem is that the robotic printing doesn't allow it. Sure.
Mm-hmm.
Sorry, just to make a last comment. That's where the conversation of the column and the tree that you again didn't mention was really interesting previously. And that is the tree doesn't only vary vertically, massively, because of the branching and the density of the trunk. And that's not only a structural issue, it's also a capacity of collecting water from a very large side, and light, obviously, but collecting the water and running it down to bring it down to the roots. So that's on one hand. On the other hand, you cut a tree trunk and you have a very different composition in the middle and on the outer part. So how the bark starts dematerializing as opposed to the middle where the water content is sort of brought up and down is very different. Here you didn't have that, means that that density wouldn't be all over. It probably would be much more of an edge condition. Once you get into the middle, you get much more of a solid condition. Means that where there is a structural density that you want to maintain. But clearly, these are sort of nuances that currently don't come across. Also, because this, in a funny way, it's wrongly placed. It should be, in fact, hovering here. I mean, it's very heavy, so I understand, but it actually should allow us to think in that mode that horizontally there is a gradient as much as there's a gradient vertically that is inherent to this work.
Did you make a comparison? Because I think the material you're competing most with is concrete, right? Did you make a comparison besides structural capabilities, like energy intense or energy requirement for production and stuff like this, or a cost? Because that would be interesting if you try to compete with a material that's already very highly present on the market. How do you I think also energy requirement would be interesting because I think the concrete production requires a huge amount of energy. And the color.
Actually, I tried to control the color somehow because with the proportion, so you can see this like more brownish. But if you touch it, it weathers off. So I mean, you can control it with the composition.
Just the last thing, I think is coming back a bit back on the first comments, but I think about the resolution of the printing. You were saying that maybe you don't succeed to have the same resolution inside, but I think there's actually more resolution here because the way it's dripping and creating even more surface by the way it's doing, and there was variety actually. When you fabricate it, you have like many different parameters that you could control and tune, and actually these things that you want to maybe may have a gradient from the inside to the outside. Maybe you want to actually have this leaking happening in the inside and filling all the gaps and having really a core really strong, while the outside you want it a bit more strong and like droplets and getting as much texture as possible. And the same as you're making the comparison with the trees, that actually the structures is not only for performance, but it's also for the way it's constructing step by step. I think the same will happen, that you need actually maybe a core a bit stronger or multiple cores. And I don't know, for me, this is a pattern that you don't see as just like a central diffusing, but it's really like mapping a huge surface, no? And this could be like spread much more. And you have really this central system that you imagine as a column. Well, I imagine this as much more growing in a vertical, horizontal manners. So having as much as possible, maybe some pieces going up. But I think you're more speaking about like a 2D surface and actually a 3D vertical one. And then sometimes there's some peak going up. But I'm quite surprised that you finish with this shape at the end. No? The top one, you look like you're waiting for a bridge to go on top, or something that is like another infrastructure that will go on top of it. Or maybe you can imagine how you can combine with humans. But it looked like, okay, but it looked like that you're going to make a production that is actually not suitable for humans. Now you're looking at pH that are quite different. The sulfur might be a bit good for the skin, but the smell is quite strong. Generally, people don't like it so much. And then you have to collect the gas that's coming out from the algae. There's many things that I imagine this more like a separate cultivation land that you have maybe in desert, or that you serve as a barrier between the desertification expanding to the city, and you have this farm that actually has an edge in between these things, no? And then suddenly you will have a side that tries to protect from the sun, and a side that is oriented towards the humans, maybe letting them get in inside, collect, clean. How all this flow could be actually a good drivers of your design.
It could still come into the construction field, where you start thinking about the structural properties, you could still use the foundation material, only for foundation. Then we miss out on the
But as interesting, so I will not go into the reason.
But I think in general, the context is missing. I think I've lived for 1 year in Taliesin West, and when I found out how Frank Lloyd Wright came up with the idea of his concrete, that was amazing. And it was just coming from the context. I think that in general, in the process of this project, there is too much design. And you never question a context, because I think this project might change if you bring it where I'm living now, where more than collecting water, we want to collect dust. Because we live in the kingdom of dust. And this dust is not even like the Sahara dust. It's the Sonoran Desert dust that it's crossing our land and going to Alaska to destroy the glaciers. So I'm looking at this project and I can't stop thinking that this would be a nice collector of dust. And it's so quick, the process, that it would be amazing just to petrify that dust into a new configuration that doesn't depend from a printer, but from nature. So I do believe that I saw many of these things in nature. So I'm wondering, what are you adding? I think your combinations of material is what is very, very interesting. But what happens when that becomes a landscape and it's not, you know, a design thing, just because we need to get a diploma out of a school? And now that you're going out, I think, come over in Arizona. And after, I mean, you can test into our very extreme weather, 48 degrees right now. And this dust really like destroying everything else. And try to understand how to design with nature in that sense, because I think this is a good beginning. But if we can collect the dust, we can finally have water. And I think what is very amazing, probably, the way to go out from this, you know, loop is like, but what context? Because that stuff built for Taliesin West doesn't work in Chicago or in Spring Ring. If you go to Taliesin, it's completely different. And he came up with the idea because the earth and the sand that it after tested into a special color and the lack of water, I mean, invented a new material, and out of that material now we're doing other stuff. But I think I really miss a context, and I was surprised by your confusion in the explanation, and I understand that you are so much into your material that sometimes it's like we need to put kind of rules and say, how do I get far from my material? And instead of having a pizza, pie, this and that, like, how can I use this to stop desertification, for example? Because it is all about sand, if I'm not wrong. And so, again, and this is for everybody, how do we put questions to our project? Because here we can tell you whatever, but you will be without us. How do we put a question to our project in order to have the project to go farther and improve?
Follow up something, which is I think different students have different intentions in a master's, and surely in this one. And the way I see Kunal as a student is then he didn't see this year as a place or a moment to create synthesis. I think you saw it as a moment of incubation. It means that you needed a year to be very much in sort of one mode of operation, with all the possible critiques around missing context. The explanation about how many gases it produces, etc., are not completely there yet. Manufacturing has problems. But the need of being, for a period, encapsulated in doing something that needs its time, and then is prepared to get out these other bigger, grand, critical questions. And I do appreciate that. I think some students are looking for synthesis in a master's, other students are looking for a moment of incubation where they don't care about synthesis, but they need that time because they won't have that time later on. And I think the school is allowing these two different operations to happen simultaneously, and mixes obviously between both. And I see that this project having exactly had that virtue. I didn't ask for the context because I felt it was actually asking too difficult questions in a process that can't answer them too early, but it needs the time to go on to find its own rules and its own difficulties and limitations, so that you now have the time to take that further, get more involved with the American Association of Sulfur Production, whoever else is dealing with extremophiles like those, etc. Dust, for instance, is a fantastic process for bioreceptivity. It's one of the quintessential drivers of bioreceptivity, because the dust deposition is the one that allows then small species like mosses to thrive, because it gives them nutrients. And that's why urban environments often are better than natural ones, because there's more dust in the urban environments. In some, obviously, you have areas of desert, but in areas like urban environments like ours, there's so much of a complexity in the air. Our air is very heavy due to the pollutants and the dusts, that the deposition of them is hugely bioreceptive. So this is obviously a fantastic dust catcher. I see again, this is a seed, as a grand seed. I think there's a lot to take further that I hope you are not going to leave behind. You're not just to park it, put it in your portfolio, and start designing toilets in a shit office. I seriously hope that this is becoming something more meaningful.
I think, as Carlos, as Marcos was suggesting, this deserves a development. And what I will say is the structural capacities combined with the reactivity will be for me, interesting thing. So I have 3 suggestions, and we have to try to look back a little bit to the history of concrete. That probably is something that you have missed as part of this. The first thing, I think, for making this a structurally resistant material, the first strategy will be what the reinforced concrete did. That was combining a material that was able to deal with tension and a material that was able to deal with compression. That was mortar plus iron. And then the problem with iron, you could add iron fibers to this, but probably it will be reacting to sulfurs and algae, and it won't be a very good idea, because it will be a chemical. But nowadays you have fibers that are super interesting and cheap, that are glass fibers and polyester fibers, that are having a very good performativity structurally, and that could create something like reinforced concrete out of this. And I'm sure polyester might react with sulfur, but glass for sure is not reacting. So for me, let's say, path of experimentation number 1 will be adding something that is making this resist not only compression. You told me you can stand on that. Yeah, but I could break that with my hands, making a real combination of compression and tension. So if you add something that is resisting the tension, and you allow the material to resist the compression, that will be adding fibers, glass fibers. I will be very curious about that path. For me, the second one will be what Eladio Dieste, Félix Candela, and usually people that are coming from poor countries are doing with concrete, that is making very thin layers of that. And basically, the way of dealing with that is dealing with the geometry, so that the thinner layer is the most resistant because of the geometry. That could be done with this identically. Of course, if you have gone for the adding of fibers, good. But also Gothic has this combination of very thin layers combined with nerves. So maybe if you come to structural nerves that are loaded with fibers, and then cladding, but that can be a structural, that can be a dome, that can be a quite horizontal dome, I think you could go with that. I think I always feel like really disappointed in a way when architects say, this is just cladding. Come on, let's go for it. You can do it. It's just adding a bit more. It's maybe combined with nerves. And I think the third suggestion that could work very well is going a bit in the direction of Le Ricolet, and not only Le Ricolet, but the nowadays hybrid structures. That is, after understanding how a big truss work, or how a big beam, and how concrete and steel collaborate in detail, now you can really understand that. You can even have very detailed graphics on how the movements are happening. What many people are doing is separating, again, elements that are just compressed with elements that are just tense. For example, making a beam combining concrete pieces in the cords, in the joints, with metal pieces or cables that are just tense, and you have to be very, very accurate to know where everything is. So I think combining these with materials that are allowing you just to enjoy the compressed capacity that this material is having, probably after adding the fiber so that it has a bit of capacity of resisting tension, could be a very interesting thing. And my last comment is, every structural system has a typology of a space that is associated. For example, the idea of an structure made out of beams, for us, is very natural and very, let's say, normal and average, but it's coming from concrete, reinforced concrete. It's coming from the 30s. It has a birthday. So which kind of typology with this idea of bioreactivity you could do? I think, for example, thinking in doing domes that are very much more horizontal and in which you can increase the span so that it's exposed to the weather in a much bigger surface, and developing a little bit like Felix Candela research on thin surfaces, and all of this could be very, very interesting. And the materiality has the capacity. It's only that sometimes I think when architects think into systems, they tend to think that one material is going to solve everything. And systems now are hybrid. Look at around. This is metal, this is plastic, this is concrete, this is brick, this is metal. This is what is happening. So I think it's a combination of materials inside and structural strategies, but it could be really, really interesting to make this more thoughtful in terms of structures, I think.
I'm sorry for...
Thank you for now. Oh,
Unless you want to hear.
Yeah, I want to hear.
Thank you, Kunal. Oh, it's fine. I'll say one thing, which is, I will because he's just asked me, and I will respond. So, context is very, very interesting here, and I think the synthesis of context comes out. I'll try and do 3.4 million years of history in a minute. The cracks in the earth, where the interesting materials come out of the earth, give this exquisite wealth of diversity of materials and also of biota. And you seem to have had a synthesis and captured the context through the materiality and the biota that you've chosen. So around those volcanoes, around those cracks in the earth, that's where the sulfur comes out. That's where these algae are growing. And you've taken that moment in time and space and made that your material concept. So I find that to be successful. It's exquisitely primordial. Well done.
Hello. Hi, my name is Jessica. I'm from Mexico, and my project is called Design for Aging Buildings. We're thinking Mexican render techniques in formal climate responsive tiles. I want to open my presentation with a very interesting and inspiring quote by Gilles Clement, which says that we always, calling the architect looks like the only way to deal with the natural disorder we find in nature, and that we never see this as a possibility to generate new ideas. But is it a real natural disorder or just a biological order that we don't fully understand? I'm going to start with a case study. These are traditional housing in Monterrey, Mexico, northeast Mexico. And what a building always tries to be, it's this building that looks that it was just made like 1 year or 2 years ago. It tries to always keep or maintain this clean, pristine, and homogeneous surface that it looks almost like a sterile, and it takes a lot of effort to maintain this image. But what the buildings after years they end up being, it's this image in which the environment conditions take a part of the equation, and after 20 or 30 years we have this. Yes, and after, yeah, probably. So what are the characteristics of these buildings after the environment has done the work in it? We can, the pointer, oh, it's here. If we see the urban grid of the Monterrey, we can see that we only have box-shaped buildings which don't respond to environmental conditions at all. So we have erosion, biodeterioration, and bioreceptivity in these surfaces. So I was trying to understand, according to the environmental conditions in each facade, what are the characteristics that you can find. For example, I started analyzing bioreceptivity in the north, east, south, and west. In the diagram here, we can see how small species grow more in the north and the west side of the facade. Biodeterioration, we find it more northeast and southwest, as we can see in the images. And erosion, we can find it more in north and south. So as next step, I was trying to compare what are the environmental conditions that I have in each of the facades and what are the characteristics that the environment leave after years. And I was wondering if it's a real state of decay or is it just nature doing its job after years have passed. So I took if we take a section of one of these houses, we find that they build with a traditional construction technique used in Mexico, using adobe, blocks of adobe. And as a finishing, they use a lime mortar with the natural additives, which takes me to the second part of the presentation, which is the matter. I'm analyzing what's the lime cycle, since they're using lime mortars. And what is very interesting about this material is that it's a closed, or it's a complete cycle, which it comes back to its original chemical composition once they take them out of the quarry and after it dries. According to the characteristics that you want to give to the mixture, you use natural additives. These are some of the ones that we used in Mexico: sugar, protein, or fat. And the one that we used in Monterrey is a cactus mucilage, which gives more plasticity, adherence, strength to compression, etc. So one of the most important things about using cactus mucilage is the extraction of the liquid, which is used instead of water in the mixture. When you do the mixture, you use sand, lime and water, but in this case, we replace water for cactus mucilage, which is this sticky liquid. So I did some material tests and how can we start playing with the porosity and which shapes can we achieve with this material. One of the main problems of this material is that it takes a lot of time to dry, and it actually needs a lot of water during the drying process. So as next, yes, this tree, sand, yes, yes, yes. So as next step, I've started wondering how can we, how can I say, how can we start playing with geometry according to these environmental conditions and wind, water flow, etc. And I found a mathematician that has this book called Sensitive Chaos, The Creation of Flowing Forms in Water and Air, which is study what are the geometry created by the fluids in 1962 actually. And as a main intention for the project is to play with aging process, more with material, biodeterioration, erosion, decomposition, vulnerability, analyzing the fluids and the sun exposure which cause these conditions, wind, water, and sun. We have some required conditions to be able to control these factors, which are turbulence, collection, distribution, and retention of water, shade for sun, and as a geometrical strategy that we will use to create these required conditions, which are wind barriers, chambers, channels, porosity, etc. And these are translated to topological operations in terms of a surface, where we'll create relief, patterns, and foldings. And as a consequence of all this, we will have growth. And for growth, we need to enhance a bit with geometry as well, so we will create cavities, fissures, and holes. So in terms of geometry, I've started analyzing what are the patterns created by the water, playing with vector fields, applying different forces to the vector field, and these are the shapes created by opposite forces in the vector field. Then I was playing as well with the relief. For the wind, we have some geometries that have like these bumps or wind barriers that can protect the surface from erosion. These ones that have some holes that can act as protectors in the surface, etc. I was trying to mix the relief idea and the lines of the patterns. And for the sun, I started playing with the folding since, I don't know if you know these cactus that have foldings, a lot of foldings. They have this geometry because in between the foldings, you can create microclimates since the sun only hits the top part of the geometry, not the one that is in the back. And there are some of the models that I could, I casted according to the geometries that we just saw. So here we can see how the light only hits this side of the fin and not this side. So it helps to create a microclimate in between the foldings, which cool down the surface. So these are more like strategies I was starting playing in terms of geometry to see how I can deal with this. So how can we start like putting all the pieces of the puzzle together? I'm gonna use now Joseph Maria Montaner in La Modernidad Superada. He talks about the beauty of the skin and how nowadays with all this data and all this information that we have in the environment, we should be able to design facades that they're not only like but they should be different according to the orientation, and the function should be different according to each orientation. So as a reference, I was looking at the projects that helped me to understand this 360 degrees condition that the building should have instead of being a box, as we see in the urban grid in Monterrey. How can building can start like taking shape according to the environmental conditions? So the first one is the Sumaya Museum in Mexico City, that it gives more an opportunity to play with this idea of changing each facade according to the environmental condition. The second, it's like a donut-shaped building that we find in the Monterrey, the university, and how they have like this pattern that it's only like a art piece. It's not doing it doesn't have a function per se, but kind of give me some hints of how can I deal with this problem. And the last one is the pyramids in Mexico as well. And as we all know, they use like environmental analysis to design this. Like we have a pyramid in Mexico in which one day a year you can see how a snake of sun comes down of the stairs. So that means they're aware of these conditions and they use it to design. We have another example as well in which once a year you can see like this chamber inside the pyramid. It has like a lot of light, so it tells them when to do some rituals, etc. So all these examples help me to try to understand what should I do next. So here the proposal is, instead of having this box shape, how can we start shaping this this geometry of this building according to the environmental conditions? These are the diagrams that we saw at the beginning of the presentation: bioreceptivity, biodeterioration, and erosion. So according to these conditions, I've started analyzing what are the impact of the sun in the surface. So I've started using this Galapagos program to see what's the best condition possible for heat exposure. Is the first one, you can see a lot of changing, but in the second one, I've just choose one and start making very small changing. But by making these very small changings, we can see a big impact on the surface just by tilted a bit the surface or changing the curvature of the building. And as we can see down here, this is the temperature chart in Monterrey. So during the whole year, we have a lot of heat. So the next analysis I did was the impact of the air in the surface, which is very important. As we can see the erosion diagram, we have a lot of erosion in the south and the north, given that the main wind flow comes from the south. So this is the building facing the south, and we can see how in this part it's where it will receive all the impact of the wind. So this will start giving me some hint about how to use the geometry I analyze to start making this gradient between north, east, south, and west, and how each facade should behave different according to these conditions. These colors are showing the air pressure in the surface. So as a proposal for the surface, I first created a pattern that will change from north to south. In the south, we will have more of a relief. In the east, we will have more of a shading, since it's where I need it. In the north, I will try to play more with the cavities and holes to enhance growing for the small species. So after I created this pattern that will take me, or this flowing pattern that will take all the water from the south to the north to all the holes, I have channels, and I have the cavities, and I have the foldings, and I have like a juxtaposition of geometries that will help me to have like a multi-dimensional performative surface that will allow me to allow a lot of things to happen at the same time. So this is the result after all the operation or the topological operation to the surface. Whoa, missing one, yes. And so, more or less, it will look something like this. And I'm sorry, and the last part, but not least, is the fabrication process of the pieces. So this panel, I'm dividing it in 6 pieces, but since they're big pieces, it was very expensive, the process to use the silicon to produce this. And since I'm arguing that each piece should be different in each position of the surface or the facade, the pieces have to be unique. So to make this process with silicon will be too expensive, since a silicon mold will cost like €1,000. So I need to find another technique to be able to build 1,000 pieces with unique pieces. So I've started experimenting with natural materials, and I found agar-agar, or it's a jelly. So I'm making molds out of jelly to produce the pieces, and mold can cost like €10. So I'll decrease a lot the cost to produce one panel, and that can allow to produce the different 1,000 different iterations with the same price and one silicon mold. It's the same as silicon mold, but I can destroy it after, or I can just reuse it actually. Yes, and it gives me like, I don't know if you can see it in the picture, it gives me, no, of the jelly mold, no. It gives me all the texture, like it takes the shape of the mold that you give it. So it's and 90, like how you make agar-agar, it's 98% water and 2% of the material. So my main material for the mold is water. So I think that's it. State of decay, or nature doing its job. Okay.
Thank you, Jessica.
Exactly.
Stop looking at mobile phone thing. You don't have to.
Okay. Okay, so here is the prototype of the panel or the surface. So here it's a transition from south to north. Yes, it's unfolded. Like the surface, you can see a transition from south to north. I'm sorry. In the south, we have much more of a topography with these wind barriers and more of the texture. So I can create turbulence in this area. Then we pass the east side, which needs a lot of shading. So we can see here the natural strategy of the cactus and the foldings, how the sun hits only this part of the surface, and it creates shading in this. So when the water flows down, it can create a microclimate and control the heat exposure in this area of the surface. Since it's the east, west has a lot of heat exposure. And if we look at the whole pattern, we can see these channels that they're all going to the north, in which we have the cavities for the plants to grow. So all the water in the surface will go through these channels to arrive to these holes. Inside the holes for the plants, which are like almost like pots, are like small pots for the plants to be allowed to grow here. We can see an internal texture which will allow the roots to be able to trap inside the hole. and it has some protection from the wind, since in a very small scale, plants need air control for the wind. The wind impact of a very small scale, it's very important for plants to grow. So, yes, I think that.
Start by saying a few things, and that is that I think it was impressive to see of how many layers this work has. It sort of keeps on going from references of Gilles Clément, which is about landscape architecture, to structural references, poetry references, environmental references, even down to the Mayas and their cosmological understanding of the world. I seriously think that as a process, the idea of the synthesis, as opposed to the incubation period before, I think is achieved. Seriously, you have achieved the level of synthesis of these different layers that I think is remarkable. And this piece is to be understood like that. I see it as a snapshot of something that probably will be much larger. And as you said, it's unfolded, means that it's actually to be understood as being curvilinear. And in my opinion, there were two extremely clever moments in this project. The first one was when you did a very simple analysis of the grid in Monterey. The grid, this ensanche that you have in Monterey, allows you to compare the facades so well, which in other cities would be incredibly difficult to do. You could do it in Barcelona, you could do it in cities that have these grids, but you can't do it in cities where you don't have a grid. It means that your observation, by juxtaposing the facades, gave you a very clear understanding of what the context was giving you as a context. So that observation, I think, was super intelligent, and that led you to make a statement that you were designing for aging buildings rather than for decaying buildings, which is another phenomenally smart move. And it's sort of funny, you look around and see an audience of students and a bunch of teachers who all think they're still young, but they're also aging. It means that they're all thinking that they are still in their 20s, but they're actually not in their 20s, and starting to think, we are not decaying, but we are beautifully aging. Means we have the knowledge of the aging. And I say this because I think buildings that age are phenomenal buildings. Buildings that cannot age are shit buildings. So the idea that you take that as an environmental strategy, that rather than this becoming a strategy of decay, it's a strategy of, in fact, taking it as an advantage and designing something that hasn't been done, I think is fantastic. So the next step is to wait for these ones to be really made at Escofet. There was, again, a conversation with the industry. Just because of a pure timing issue, it didn't happen so quickly, because this needs a bit more time. But the summer period is now the one for these panels to be actually made, because the expert at Escofet was so keen on the work that he came even to the IAC to sit down with Jessica and discuss of how this could be made, because they are very keen to know how they might be applying this in their own production.
Yeah, thank you, Jessica. I think that the work is beautiful, and there is no doubt about this. The whole process is very rigorous, so it helps us understand that it makes sense. It's not just experimentation on the material, but it's really something that makes sense. For me, what it's the most intriguing and interesting part is the fact that design becomes, let's say, the most important agent of, on the one hand, creating aesthetics, and on the other hand, controlling the performance. So this kind of beautiful pattern, it's becoming much stronger when we understand that it is related to a specific context, related to a specific performance, related to a specific orientation, no? And the idea of aging versus decaying, I think that it is that part of the performance. I would love to see a simulation or a kind of a diagram that shows this performance in the different moments of the building, no? When it is an adolescent, when it is a bit of, of an elder, let's say, but each moment of that process has a different performance, and you are dealing with that. And I think it's beautiful to see that performance, because that could create a different interaction with the users, that would create a different function for the urban space, that could create different kind of conditions out of this aging of architecture. And I think that is very powerful.
Thank you for the presentation. It was very clear. You were able to put us, comfortably understand this. Sometimes I'm not dealing in any time with this kind of chemical things. It was very clear and very beautiful to see the context at the beginning, which was the ruin, the decay, the aging, whatever. And I'm very interested in this model because, so I'm interested in this project a lot. No, but like what to me it was important when you say, oh, I couldn't make it solid because that material is liquid, the cactus mucilagida. No, when you say, oh, but I couldn't make it solid, the liquid material, when you did the component, you say that it would dry in a long time. It takes, and I think that was interesting because the plants there are the cactus. They have this property of being succulenta because they need to be always wet. Actually, the cactus is a machine for keeping, not for exposing. It's not a decorating thing. And so what I like of this model is that there is a back, which is missing in your project. When I hike in the Sonoran Desert, all the cactus, there is a moment after 500 years they collapse. And it's very interesting to see where they collapse, but they show what is in the interior. And I think that you are fighting the box, but you are producing another box. Because I would like to see the back of the skin. And if you use that reference of Montaner and the one before too, the beauty of the skin, who was talking about the beauty of the skin? So the beauty of the skin is what is now revealing. So if I have to ask you to push forward, it's not going to Escofet because Escofet is only interested in the surface. But sometimes you can go to Escofet and say, I'm interested in the back. Because I think that what is interesting of architecture is what is inside. And the succulenta planta, it has the capacity of always having an interior condition that makes this exterior. Has the skin as the condition of the body and the organs and the things. So you are dealing in such a brave way with such a complexity. They understand your incubation. And I please ask you now to look at the back of your model and try to put a question, but okay, what else? How do I keep this water? Because if it's your reference is a thing that for the 80% is keeping water, it doesn't mean that that 20% it's important just because itself. So if I look here, what's happening, and we can see probably in, I think I saw it in a model there, when it goes inside, it gets inside. And I think that is what is making this project more tectonic and geotectonic, and more probably bioreceptive. And what is inside. And I think that is, you are such an amazing designer and architect that I think you should really start to think in having it more liquid, more, sometimes we are limited by materials, but probably there is where you have to push your investigation, because this school is probably sometimes we are requested to do these objects, but what's happening when you put together, what is the wood? you know, and intuitively, I mean, you are so clever that you understand when the things are happening. So what happening in that support? Because it is an amazing exploration, but it's still a box. Until you don't deal with the interior condition of life, life is not happening. And this is the problem of architecture now, that since an exhibition that happened in the 90s that was called Skins and Bones, that was referring architecture to fashion. We think that architecture is what Romero does in the Sumaya Museum, no? Go to Fernando, bring this project, and keep asking him, okay, let's work the interior conditions of architecture in the cities. Let's be bioreceptive with people. And I think that that to me is about decay, which I love more than aging, because things decay, especially architecture. It decays, it collapses, it destroys itself, and it goes back into nature. In that moment, nature needs to receive it. And so I'm so critical because you are amazing. And I would like really not to have you go in and work in 3D things, but like to push this forward and making it interior and making it a skin, which is both sides.
Okay. 3 suggestions, and some man might bridge the gap, maybe with Selena. My first suggestion is thinking about the inhabitable capacities you are creating. I think it can be understood as a next step, especially with the 360 strategy that you are creating. That is a quite, nobody has mentioned till now, but I think it's really changing the rules. And it's specifically changing the rules of the 4 orientations, because the sun is not having 4 orientations, but 360 degrees. So what I will try to look at is, first I will maybe look something about biophilia, and how for many people trying to make it compatible, the layout of the programs inside of the architecture with a much more coherent ways of enjoying the natural light is something that is on board, is on many people's tables. So maybe thinking that you can organize a program in a kind of circular pattern, so that you can have exactly the moment of perfect light for each action. You have many examples in history of circular buildings trying to do that, but can be quite interesting also to mention that this is taking you to a perception of the interior space that is usually more intuitive for the user, because users tend not to pack actions into rooms. That's what architects do. That is saying, this is the living room. Life of people is usually much more continuous, and they perceive time in a much more continuous way. So there is a lot of reading about biophilia and how our natural perception of time, space, and light is continuous, and how you can make continuous buildings, let's say, inside of this system. Then second suggestion, I think when you want to go to pure and three-dimensional buildings, tiling is better maybe than making boards. So I was thinking that maybe tessellating a little bit these boards, so that all the singular effect that you want to create with the hills, canals in 2 directions, canals in just one, holes protecting from the wind, like you have mentioned, like I would say 7 or 8 effects. Maybe they could be a tile, but this combination of tiles could much more, maybe be a bit more flexible, adapting to different situations. And as I was saying, it's again an opportunity for structural resistance, because you could do bricks that could be supportive in each other, and I think it could be a very interesting situation. And I have 2 more comments, very briefly. I would recommend you to read Bruno Estaño and his book, What is, or How it is, I think it's What is Tropical Architecture. And in this book, he's saying, in tropical weather, a wood facade is always consisting of 4 meters depth, because you have to have a change in the floor, then a canopy, then a louver, then something protecting you from the rain, then the real glass, then the curtain, and inside you have still vegetation. So all this happened in 4 meters. So I think maybe also a very, very beautiful exploration will be what happens if you do multi-layer, and it's like a collection of louvers that could enjoy the in-between, let's say, transition that is happening in the typically in the tropical architecture. And about aging, I have the theory that enjoying visually decay elements or old elements is a key question for our future sustainability, because basically architects are spending a lot of money together with the clients in retrofitting, refurbishment, things that are perfectly functional. New shops, new hotels, new universities, simply because they are a bit out of fashion. So this work on the idea of worsening of materials as something that is adding value, for me, is super clever, and the presentation was super nice.
You just add, if you add to this comment, also what Areti was saying before in terms of this performing, it would be really interesting where the erosion takes place. Do you know that the materials are not all the same density and thickness, that in fact with time these so-called pores or containing areas could become bigger or transform? In their shape will be with time changed? Would the channels be deeper with time? Do you know what is really the long-term vision for how this wall is capable of absorbing these changes of time in the aging process? And that would be something that would give a nuance to the materiality and to the geometry that would be really fascinating. Because in fact, to create a new petrified system that you wanted to keep beautiful as it is, and then 10 years later it doesn't look as good anymore, and you are sort of sad about it, you miss the point in that moment. You, in fact, I mean, we have currently a problem with like this with our bioreceptive panels in London. We put some moss shake on it, and they don't look good. They look shit. People were sort of asking me why only half of the panel is weathering. Means, why is half of the panel looking shit and the other one looks quite good? It's all this problem that I aesthetically, and in conversation with Frederick Migru quite recently, we were discussing about that. Aesthetically, we are on the verge of entering a different chapter, which is things that we aesthetically always considered not looking good, not being accepted within certain parameters, like this idea that we want newity and new things to continue looking new forever, and that the aging and the decay aspect doesn't have a space because it's seen as a negative. We don't like randomness. We don't like aspects of patchiness. We like geometric order. We like a level of control. This panel still is controlled. And we all sort of share the beauty of the controlled aesthetic complexity that it has, but it's controlled. The lack of control will be fascinating to be played out. And I think that would be, for me, the biggest challenge to the project, see whether it can be truthful to itself. That the statement of this becoming an aging system that doesn't look that good is still fascinating, and probably better, actually. But great stuff. I think it was fabulous. Somebody wants to say.
Yeah. I think I'll be very, very quick. You've made an essential extraction of the environmental parameters that affect a surface. And you've talked about aging, and we've talked about aging and the process of aging, but it's a process of change. Whether that's a positive or a negative, it's unavoidable. And you've taken those extractions, those parameters, and joined them into a conjugation which would favor growth, essentially, and seen the decay or the attachment of biota to a surface, to a wall, as the object of favorability. There was that for me is an intelligent extraction. The conjugation, the moment you've made that programmable, you use the word juxtaposition. And I think this moment of control, where you've thrown those parameters together in that juxtaposition does something else which favors growth. In ideas of biophilia and in thinking about nature and the way it works, if we can even use the word nature, is the concept of edge. It's the concept of collision. It's the most interesting thing when the sea hits the land, because at that point, life changes. At the collision points, life changes. So in your juxtaposition, you've, I think, unconsciously, or not, if I can say that, in an unaware way, made a favorable habitat for growth by throwing those parameters together, throwing those edges together. You've made the definable edge on a surface, and I think that is that's a great achievement. But it's also embracing chaos, and I think that you can do that. You can say, all right, the edges where the sun would hit here, the grooves hit there, and that controlled element. It's the uncontrolled points which I find to be the most interesting and the most successful in this as well. Well done.
Hi, my name is Zuna, and I call my project My Cockery, and I'm designing a public deck for water purification. First, I want to run a series of images. Maldives in the Indian Ocean, Kiribati in Central Pacific Ocean, Borneo in Southeast Asia, Bangladesh in South Asia, and I come back to Maldives because I'm from the Maldives and I've always been very and I've always been concerned about issues which are dealt in like island nations. Maldives is a tropical nation composed of 1,190 coral islands, of which 200 are only inhabited and 80 are resort islands. Maldives is considered the flattest country in the world, and the highest point is just 2 meters above sea level. And it covers an area of 118,000 square kilometers, but of which 99% is salt water and just 1% is land. And I put a picture of the capital city just to show how densely populated it is. The map of the Maldives, it appears as a dot on the world map, and that's the size of the city. And this is how densely populated the capital is. There is no more space to grow further. So why all these small island nations? Because all these islands and countries are faced with the same problem of global warming, climate change, and extreme weather. All this leads to sea level rise, erosion, coral bleaching, and flooding. But these all problems create two main problems, which are like the loss of land and polluted water, which are two main factors that I want to deal with in my project. And I believe that we need to adapt to living over water, and adaptation is possible, that we cannot be environmental refugees and shift to other countries or land. So this is where my project comes in, microfiltration and microcrete. So I started looking into materials which could give me the possibility to create land over water. I started looking into mycelium, the vegetative part of the fungus, which is a biomaterial, a sustainable biomaterial, and materials that are self-repairing. Materials that have a symbiotic relation with the nature, because we need to deal and communicate with the nature to tackle these problems. And the specific strain that I'm using is the oyster mushroom mycelium, Pleurotus ostriatus, which has a good growth rate in salt water, which is very important for my project because I'm considering the first prototype to be in the Maldives. It helps, mycelium also helps break down oils and toxins in water. It also helps to break down biodegradable plastic faster than the natural rate. So it purifies the water. And then I started looking into the specific features of the mycelium, where it has a number of numerous behavior which could assist in my design of the prototype, such as being a good binder, flame retardant, promote plant life, and also is a good insulator. So then I looked into how these behaviors could be incorporated into the features that I want to build. And then I also looked into ways if mycelium were applied architecturally before, but it hasn't been applied in salt water yet. So I started researching, and then I came across Paul Stamets, the famous mycologist, and he actually was the inventor of microbooms, who created the microbooms, and he uses microbooms. Actually, it's pasteurized hay in bags, which he just submerges in water to purify the water, which was used in the Gulf of Mexico. And I've been in contact with Paul Stamets, and he's been really advising of how to tackle the issue in salt water. And some of the other theoretical references that I'll be using is the Ecovative, where they use mycelium as a packaging material, but now they have come up with interior wall panels, and also the Mushroom Tower by David Benjamin and the Microtexture project by Phil Ross. And I'm also very fascinated by the project by Rachel Armstrong, because her projects are like self-repairing, and which is a very important factor that I need in my project. Then I started with my own small tests by cutting out cardboard pieces into small pieces and then soaking it in salt water, boiling it for 1 hour, and then also using sawdust to create a growth medium for the mycelium. And using stem buds, it showed that the mycelium or the roots of the fungi started growing in just 3 days. And then I wanted to compare the different growth stages, or how much it grows in salt water and fresh water. The first 3 tubes are in salt water, and the last 3 are in fresh water. It doesn't show much difference in the growth rate, so it was likely that the mycelium could be used as a medium to grow in salt water. These are more experiments that I conducted with salt water. And I also try to grow the mycelium in 3D printed wooden filaments, but I didn't go further with the 3D printed pieces. I choose another material to deal with the issue. These are also like experiments that I did with soaking the mushroom pack in mycelium pack in salt water for 24 hours, and then in 9 days it showed the growth of mushrooms, which was really the factor that I needed in my project. Also to cultivate, also to filter the water and create a platform to create land over water. These are also just to understand how the growth differs in freshwater. The top one is the freshwater and the middle is saltwater, but when two spores were introduced, it showed immense growth. And then I wanted to add another material to the mycelium to make it stronger and also to create mass for the water filtration. Then I looked into materials which could be readily available in the Maldives, which could be cheap, and also which could enhance the factor that I needed. So I chose coconut fiber, which is readily available, which is a sustainable biomaterial made of cellulose, and it's relatively waterproof. And the amazing factor is that it's less biodegradable, so making it possible for the prototype to stay longer. And it's very resistant to damage by salt water. But then, since I wanted to create land over water, I then needed a structural element to go on top of it to act as a platform for people to walk in, so for people to have land when land becomes extinct. So I looked into concrete, but also reinforced with coconut fiber. It increased the compressive strength by 13% when coconut fiber was introduced, and also the flexural strength was increased by 9% with the coconut fiber. And the amazing factor is that it could be made into thin sheets, so it uses less material compared to normal concrete. So the coconut fiber was the binder for mycelium and concrete. In the image, it shows that the coconut fiber was introduced into the concrete before the concrete dried, and then the mycelium was introduced to the coconut fiber, so it started growing on the coconut fiber. Sorry? How have you made a measurement of the? I didn't do the strength myself. No. Yeah. Yeah. It's very flexible. I haven't done the structural test myself yet. Yeah. But actually, one of the panels, it didn't break when we tried to stand on it. Yeah. So then I did experiments with also glass fiber to see how the strength would vary. And the maximum thickness I wanted to go was 1.5 centimeter to 2 centimeter. And it was amazing that the mycelium also grows in contact with concrete. So this was one of the experiments that I did, like casted the concrete with coconut fiber, with the fibers coming out, and then the mycelium started growing on the fibers. And eventually mushrooms started growing when I sprayed water. And at this stage, I wanted to look into the different growth stages of the mycelium, which was important for my project. So the first one is the state where I use agricultural waste and introduce the mycelium so that it micro-remediates the agricultural waste. And in the next stage is where microfiltration occurs when it comes in contact with water. And after several days, the fruiting stage and cultivation happens. So at this stage, then I wanted to separate it into, like, divide it into further two stages where I expose the mycelium to high temperature so that it dries and helps in buoyancy, which was important to be, which was an important factor to make it float on the water. And also when it starts fruiting, small insects and birds will come, and then eventually an ecosystem could be created. Right? So I also looked into the temperature and the environmental conditions in the Maldives, because it lies in the equatorial line. It has like a temperature which is within the range of 20 20 to 30. And sometimes in June or July, it goes up to 32. So it was ideal to have the different growth stages in my different pieces of modules, which I will show later. So when I started looking into the different temperature the mycelium needs, if it is exposed to light and within the temperature of 10 to 25, it would create the cultivation stage, and from temperatures 25 to 35, if with light, it could be the stage where mycoremediation occurs. If without light, it could be the stage for mycofiltration. And above 35, it dries up the mycelium and helps in buoyancy, or it helps the module to float on water. So then I started designing the module. I wanted the design to enhance the growth of the mycelium and also enhance the purification of the water. And I realized that for the mycelium to filter the water, it needed maximum surface area in contact with the water. So I started looking into reaction diffusion patterns where it will increase the contact of mycelium with the water. This would be one of the modules of 4 modules that I'm designing. And this would be how the bags would be submerged, or the mycelium reaction diffusion patterns would be in the water. When it comes in contact with water and increases the surface area for mycofiltration. Now that I have the reaction diffusion patterns for the mycelium, I wanted to have the design of the concrete panel to also have features that would enhance the growth. So I looked into field lines where the lines would channel water towards specific points to enhance the growth of the mycelium. So these are 2 of the modules that I'm designing. The first one is for mushroom cultivation, and the second one for water purification, where the reaction diffusion patterns or the mycelium grows as a pattern when submerged in water. And the first one is, since it needs light, it has more holes so that light could penetrate in and further enhance the growth. And in the second one, it has less holes, but it needs ventilation, so it has some holes, but compared to the cultivation panel, it has less holes. And the reaction diffusion patterns enhances the water purification. And the next 2 ones would be mycoremediation. It has openings on the concrete panel where agricultural waste could be mycoremediated. And the panel for the buoyancy, since it needs temperatures of 35 to 45 degrees, it has holes, a lot of holes, and also openings for the mycelium to dry out when the temperature is high. And I'm suggesting that when I put the last module, like it would help float the module on the water. When the mycelium dries, it helps in the buoyancy. So I would be needing a lot of the panels which would increase the buoyancy. So this is one of the panels that I'm casting, and also one of the panels that I'm concentrating now, where the water purification will happen as reaction diffusion patterns, and the top would be areas where water would be channeled, and also a surface where people could walk on when many of these panels are put together. And actually, this is an image that I clicked last summer, and when I say I want to focus the project in Maldives, people have asked me questions like, why do you need to remediate the water in Maldives? But it's not actually the case. This is one of the islands where people are living. The resorts, the beaches look fine. But in the islands where people inhabit, the beaches are so polluted that it needs immediate action. So that's it.
Can you just tell us something about the deck and maybe some of the smaller models? How do you see this creating a bigger surface?
Since it has like interlocking patterns at the end, it could be put into a number of panels where this panel would be the panel for microfiltration. And actually this piece is supposed to be flipped, but the mycelium did not grow well enough for me to flip it and attach it. So
that's the one that is floating, right?
Yeah.
The mycelium is like
Yeah.
merged into it.
Yeah. And this was also one of the panels that I
Sorry, and do you need this? I mean, do you have
because I need a surface for people to walk on, and later for other structures to be built on, so that it could create land over water when land becomes extinct. And also
an interesting point where you said the fibers are the same scaffold in a way for the mycelium, as much as they are a reinforcement for the concrete. So that's the continuum that you have of the material. And that mycelium was actually growing. That mycelium was growing next to the concrete. I think just to explain what is relevant about that is that the pH of concrete is far too high for species to grow on it. Means that before concrete is carbonated, the pH level is probably around 12, which is too high. So it was surprising to see that mycelium was actually growing in its vicinity, because you would expect it not to grow there. So that meant that this vicinity or this continuum could be created where you have the same infrastructural strengthening material that is a coconut fiber, but the total change of concrete as a structural one, and then the other one as a scaffolding one. So you would imagine this one as a double layer. As a matter of fact, you walk on this one, and then you have a very thin layer underneath that is intertwined with that one there. Right. When you put two of these together, it creates a hole. What is this hole for?
Yeah. It's an opening where when more panels are put together, it's an opening to the seawater, where I further look into possibilities that aquaculture could be introduced, and also different ecosystems. When I introduce the mycelium into salt water, it would bring in fishes. So I'm suggesting that these openings would further lead to more ecosystem and then enhance growth.
So may I ask something? Because I find very interesting the different, let's say, responsiveness in the different temperatures. So what happens when we are in 45 degrees and the mycelium dies?
It dies, and then it helps in the buoyancy.
So then your sink, the life cycle of your mechanism is over at that moment?
It could be reused and used for microremediation. So it's a cycle where
It's when it stops growing, doesn't build bioremediation. Or does it need to be changed?
It needs to be changed. That's why I'm suggesting that it's panels.
So
Yeah.
what's the temperature of your gray diamond?
It's within at daytime. It's within temperatures of 26 to 32, where it rises between 32 to 33 in June. But at nights and mornings, it goes up to 20.
I should say something to explain why this became a deck. there was a long discussion with the group about the applicability. And in loose terms, each of them has a site which is their own place where they came from. I have never done that actually in my 18 years of teaching life. I've never asked students to choose their own sites, but I felt in this case it was very appropriate because they know their climate and their conditions much better, and they have visited the places rather than choosing something they have never been, or just choosing Barcelona, which for some of the cases wasn't actually the right place. So this idea of looking at the Maldives, and what I was going to say was something about the deck. So the idea of in loose terms of a pavilion, of a space that you could inhabit from inside in order to trigger the conversations of what is behind, about the 360-degree architecture, because this is what it is inherently. All of them are 360-degree projects. In this case, in the Maldives, didn't make much sense because it was really a question of where do you put it? A pavilion in the middle of the sea, remediating what? How much? How much of this do you need for it to have some level of effect? So the possibility that you are placing it in a lagoon where there's a controlled amount of water to start with, rather than in the open sea, and that this deck can create a very, very large surface, a bit like what the High Line project in a way does in New York, but there is a line here. It would create a bigger grand area where in fact not only the maximization of the mycelium growth surface is happening, but in fact about this flatness. So it started growing the idea that a lot of these tourist resorts do use decks, and they make sort of publicity of the brown wooden deck going into the sea, very beautiful, and there's a sort of small hut. But the possibility that this is actually used for the locals to, in an area where there's hardly any space, to occupy land over water that can be then used for agriculture, fishing, and other activities, something that you haven't really explained in the project, but that makes the case why the horizontality of the deck probably in a flat land like this one makes sense. Now, one could take it the other way around and say, well, you said it only has 2 meters height in its highest topographic point, so you would like probably a project that is very vertical, but then the bioremediation in the water doesn't work. It has to be a remediation that floats in between water and air. That's exactly this layer. And so this variation that exists here makes the project be this horizontal surface. It's an interface in the in-betweenness of water and air, which explains the deck.
What I find really interesting is to propose a scenario, like a vision of where you actually see it as in the future. Because I mean, the problem is that the coral reefs are decaying, the sea level is rising, so the Maldives will disappear. Like Holland is going to disappear by 2050. That's what I read somewhere. If they, so what is your vision? Like, is this like a floating platform? Is it replacing the existing island? Will it be anchored, or will it be floating around different units that can connect? Is it a totally different kind of culture that people live on these things, and what are they building on it? Is it related to the mycelium, or is it just what they build right now, but only on a different surface? These are questions that I would find really interesting. Like come up like a vision of how this new type of living would work, rather than just putting it into a enclosed lagoon in a safe place.
Saltwater mangroves, and then take it into shallow waters where I can further experiment or see how much it filtrates the water. So first, and I also was asked the question: would it bring in other effects? Like, would it bring in other side effects when I introduce the mycelium? And it seems that right now, Maldives has a resort where they culture mushrooms, but only for the restaurants to eat. So I've contacted them, and then they're really interested in further developing the project, like testing the project in the resort first, and then take it to the shallow waters of nearby islands.
I think it would also be interesting if you develop like a kit or a set of
Yeah.
that actually locals can grow their own mycelium, build
Yeah.
platforms, rather than having
Grow it yourself.
Yeah.
And then just connect one another and
I think it's, I mean, they are all super interesting projects, but I think this is very, very special in a way. And I see a lot of potentials in further development as you can, we can hear that is around in all our minds. First, what I will say is I will make a small research on the scale of the tiles or the elements of the system, because I think at the moment there is a very good proportion between the weight and the weight of a person, so that potentially it's easy to transport, to locate in place, to tow with a boat. There are certain actions that are possible because of the dimension and because of the weight. So maybe investigating a little bit how big you can go without losing these capacities can be quite interesting, and see, depending on the transportation method, how far you can go with boats and with man active boats and canoes, and how you can tow this and all this. I think that could be very, very interesting. Second, and I think this is in a place like Maldives, very, very Maldives, very interesting, is the relationship between the organic aspect of the material and the, let's say, artificial aspect or mineral aspect in the material.
reality. There's a moment where you go into reality, you should apply for a grant and really now finally meet with our clients, which are society, people that needs to relocate, for example, identity. That would be, the only critique, but it's a constructive critique. I think you have an amazing opportunity of getting these grants, and sometimes these grants are $100,000 that you can bring back to the YAC and push forward this experiment. So don't go into whatever office do in 3D. Try to really put your capacity serving, a real need of relocation identities, because this is what is happening when we are going underwater.
Thank you. I think that's great. Okay, thanks.
Working now.
Okay, great.
Gracias para venir. Gracias. Hello everyone, I'm Nina, and focus of my research was exploring possibilities of responsive architecture, but in a more biological way, to say through microbiome of the building. So, as it goes from the microbiome, every person has its own. It's a collection of all bacteria and all microorganisms that are on our body in our body. And the term bacteria usually carries a negative connotation, but there are very few harmful bacteria. Most of them help us in living. And our microbiome affects our immune system. It can support it and harm it. And same it goes from the building. The microbiome and the bacteria that are on the building are helping or destroying our health. And this is something to be considered. These photos are photos of a petri dishes of bacteria samples that are gathered around us. So these are the bacteria from the handles, from the chairs. So they're here now. And we are so greatly outnumbered by them. There's so many of them. And at the same time, we put so much effort to try to fight it. There are so many products that are antibacterial sterilizers. And also, as it goes for our architecture, always the greatest effort to make it sealed, to make it hermetic, to make it well isolated, not hostable to any species. So the aim of my research is to design a system where bacteria is welcoming and where we can use bacteria as responsive elements in architecture. Of course, these responsiveness, as it comes from the nature, it's much slower than some responsive architecture that we are used to seeing around. So because we don't see bacteria, they're all around, but we don't see it, I was looking into ways to make it recognizable to human senses. And that's why I focused on color changing. And my aim was to design something that responds to environment and changes color. And that's the color that is growing. And I know, and also scents are very important. And I know that it might sound a bit silly that I'm talking about scents, that I'm talking about colors, when it's much more important to talk about walls, to talk about structure. But also pigments and scents, they're coming and they're based on the fossil resources and they're based on petroleum industry. And when we run out of these resources, we will miss colors and scents as well. And we could actually have them growing for us. So very important part of the research was exploring geometries and surface properties welcoming for bacteria. So those are usually the surfaces that we avoid. And these are just some of the initial geometries exploring the idea of different textures on the surface. And much of the research was focused on finding this rate and this scale of the surface texture that could be inhabitable by bacteria. Because I'm talking that I want to make this responsive to the environment, the link to find it, it's not so easy, but also some of the geometrical explorations were in terms of seeing how different orientations need different patterns and how we can feed that bacteria and how we can have only the one that we want and how the geometry is different, not only because of the species, but also because of the location and the climate. And since from the beginning you saw the petri dishes, they're enclosed systems and we cannot contaminate them. But I was thinking more in terms that I can release bacteria immediately. And then some geometrical explorations were in terms of how to protect that bacteria through haptic variations in the surface. Other tests were done with materials and this scale of the pattern and scale of the geometry, and how this affects bacterial growth on the one hand, but on the other hand, how it affects our perception of the space. At the beginning, in terms of materials, I was looking into soft materials, spongy ones that really are good for bacteria, and the other ones that are bio-based, bioplastic, and so on. But as it turns out, they are too much welcoming for bacteria, so there is always some contamination. I have them all. When we walk and we breathe, we contaminate everything, and that's not exactly what we want. That's why at the end I decided to work with ceramics, because ceramics gives me two possibilities. One, based on the mixture, it can absorb water or not. And on the other side, with the glazings, I could control where I want absorption and where not. And furthermore, I choose a technique called slip casting, that is casting in plaster blocks, which I will explain more in detail later. But this method gave me very high resolution surfaces. But also, there are many challenges, which I will talk soon. As it goes from bacteria and their response, there are some naturally occurring bacteria that are changing colors. This is Streptomyces silicolor. Its habitat is soil, and it basically secretes an antibiotic antiurodin, which changes color because of the pH level of the surrounding. As you see on these two lower petri dishes, on the left one, when the pH is neutral, it's blue, but when there is another species or when in the surrounding there is a species that is more acid, it turns to pink. There are also ways to genetically modify bacteria. Most of them it's lab E. coli because it's the easiest one to manipulate for the microbiologists because they know so much about it. So we could genetically modify bacteria and have it already with the color. We could also add enzymes that are changing color because bacteria is breaking the substance in the medium, or we could have a selective medium that is changing color. So as many of these bacteria are not available to us architects and it's not easy to work with them, I was trying to find a way that I could work alone. And I was using anthocyanin. It's a water-soluble pigment found in many plants and many fruits. For example, red cabbage. I extracted the red cabbage and I was changing the pH level of media as bacteria would be changing when it grows and secretes acid, and I would get color variation, which would be based on the speed of the bacterial growth, which is controlled by the shading on the surface. But doing these tests, I discovered two main difficulties. One of them, first one, is contamination. These are the upper ones, bacteria that we don't want. And the second one is drying out when it's kept open because they need moisture to grow constantly. These don't appear so much colorful on the wall, but they're changing slightly color depending on change of acidity of environment. And as you can see here, I have one contaminated part and one not. So the one that is not contaminated, it has a bit higher, bit more acid pH level, which means that most of the bacteria doesn't like it, and the bacteria that we breed and that we have on our hands cannot grow there. So I decided to go with this a bit acid food, agar for the bacteria. And I've decided to work with the bacteria called lactobacillus that we can easily find in our yogurt. So it's very harmless and easy to work with out the lab. And the only thing else added is an enzyme. So when bacteria is growing, it breaks the enzyme and lactose and it changes color. So the bacterial world is amazingly big, and in the labs, in microbiology labs, there are so many already done bacteria that change color according to pollutions and according to everything, which is not available to me. So I decided to work with this one that I can manipulate to test the surfaces and to prove that bacteria is living, because once we have it living, we can go further from there. And these are the tests on ceramic pieces to see if it can grow on ceramics. So as an environmental case study to link it to the environment, I have chosen Belgrade, which is a continental climate that has that often has rain, so it provides enough moisture for it, and to have a departure point for the design. This is also, as other of my colleagues working with 360 degrees, this is a pavilion that has inner and outer surface, and that the inner one actually is open and it's completely exposed to sun and rain and environment, and the outer one is the one that contains bacteria that is not directly exposed to rain and that is completely in the shade. And also many studies were done about the wind analysis, about direction of the wind. So which wind which side the wind blows when it's raining, so I can collect the rain, and what are the direction of the most dry wind which I should avoid for the design. So the prototype exhibited here, that is often called final, but it's more appropriate to call it prototype 0, as there are so many departure points from there. And it's a double-sided system, a double-sided wall. One wall is exposed, as I said, to sun and rain, and it has this geometry to collect the rain and to make it, to lead it to the spaces where I need it. So this is this side, and the water goes, there is a void that keeps the water in, and glazing is not there, so it slows it down and absorbs the water to the other side where bacterial growth is happening. So with the overall geometry, I provide the collection surface for the water and a bit and protected surface for the bacterial growth, which is in shade, and the other one is helping another to keep it moisturized. When it comes to fabrication, I had a great support from Ceramica Cumellan. They never say it is impossible, even then sometimes I think they thought it was. So about the slip casting technique, it can work only with plaster because plaster is absorbing the water from the ceramics, creating the wall around it. So the first step was to make the plaster blocks, which are extremely heavy, and because they are heavy and because the CNC machining, which I was doing later on the blocks, was taking so much time, I decided to already in process of casting these blocks to preform them, to make it weight less and to make the CNC milling machine less. So this is a diagram. I would first make a wooden frame with a fabric that is stretched, and then I would apply a thin plaster shell, which would give it this shape of fabric formwork. And then I would flip it and build another frame around it, where I put around 17 to 18 liters of plaster. And then it would become a block with this shape inside that could be taken out. And I already have a pre-shaped form from where I could go to the milling, which optimized milling time from 5 to 6 hours to 40 to 60, 80 minutes per mold. So these are some images from the CNC milling, and this is the image of all the molds ready and brought to Ceramica Cumellan to speed up the drying process because of the thickness. And also here in the bottom you can see this small timeline which is showing days and weeks to understand how slow the process is. Because these molds without drying room would take 3 weeks to be dried. These are images of mold after drying and cleaning up, both sides. And then these are the double molds which join together before the casting. And this is the detail of the touching point. So when ceramic goes in, these two touches, and when the water is in these ones, it absorbs and leads to this part where the bacteria is present and need moisture. This is the process of slip casting. So the first step is to put them all together, put the ceramic paste inside, and wait around 4 hours to have a wall thickness of 8 millimeters. Then you turn it over, you let the excess clay slip out, and then you leave it like that for another 3 to 4 hours. Then you are ready to take out one side of the mold, and because of the size of these plaster blocks and ceramic pieces, it's a bit tricky to find the proper time to take it out, so the ceramic is not too attached to the plaster, and on the other side that is not too soft that you can manage, that is manageable. And after 3 hours you can take another side as well. After that it goes for a drying for a couple of days until it's completely dry, and then it's glazed on the places. This image shows a glazing piece for bacterial growth that has glazing on the ridges but not in the deep fins to let the bacterial growth happen. And as it seems as a very linear process and straightforward, the reality behind it is more like that. And probably if I was doing this alone at IAC, I would think I will never make it, but in Ceramica Cumelia, they were passing by and saying that this is normal, it happens, and that every mold is very specific and you need to find the very proper time to deal with it. And with every iteration, we were learning something new. And then after it is finished and glazed, it goes to the firing, which takes around 24 hours, which leaves us to the final piece that is here, as I said, the departure point to see could we really make bacteria live, and could we really grow our pigments and our sands, and could it really reflect our environment? Thank you.
You should go there to have a look. But before we actually move, I wanted to say a great thank you to you, Tony, because I mentioned that in the introduction, that several projects were based in this relationship with industry, and that the industry is open to support these projects that are student projects is in itself a great thing. In fact, I was whispering into Ichascon's ear that this is something that you can do here. You, for instance, go to the United Kingdom, it becomes extremely difficult because there's so many hurdles, bureaucratic hurdles. And it's something that I think we can do here because there are people like you that have the generosity, the curiosity. No, it is. And I think the fact even that you came to her presentation is the sign of this relationship and this great openness and generosity to support those who are coming to do the work with you, hopefully in a few years' time. So thank you for having the possibility for her to show these images, which make us all look at it, think, oh my God, I would love to do that in that space there, because there's some beautiful facilities to do some amazing work. So thank you.
For me, it's very important for industry, the contact, speak with students. It's possible to change the ceramic. Huh? Excuse me, I speak a little English only. Huh?
Let's look at the work there. Let's have a look at the work. Maybe quickly say something about the small people. Can we open it?
No.
We can't open it?
No.
We can't open any of them.
So these are some of the tests during the year. These are the bacteria samples around us. And all of these were tests for having insight about what could be done with ceramics and what is the challenge that we find there. And actually, this one and the opposite side of the wall here is the most challengeable one, because if you imagine this piece and it's in the mold, and the clay, as it dries, it shrinks. So the distance here starts to be smaller, and it grips the plaster. So it's very tricky to find a way, to find the time to let it out. So the most difficult part in ceramic industry is something tall and thin. So this one and the other side. And every time there are many attempts until you realize, okay, 4 hours and 15 minutes, that's the right time for me to take it out, but not to deform it. Because many times it happens that it shrinks, it grips the plaster mold, and it destroys it. It's basically, even if it's in such a soft state, it becomes stronger than plaster. These are the studies that are done about the scale issue and perception of it, and these are the bacteria. So This is the color, the same one that is on the wall, but it has been here for longer time. So it is spread all over, which I hope will happen on the wall soon.
I maybe should make a few comments, and I follow up of another whisper that I just told Ichaskun, which for me, this project was for large chunks the most difficult project. It was really difficult because there were no answers to the project. We didn't even know exactly what it was for a long period. And what I did for a long period was just to calm Nina down that eventually it was going to be a great project. But give it time, don't get desperate, keep on going. And it's a very odd thing to say to somebody, keep on going, when the person wants more answers and wants to know exactly why and what she's doing. And you don't have a lot to say, you have lots to discuss, but actually you leave the day thinking, I haven't said a lot, I haven't really made a lot of comments and given a lot of suggestions. I'm just telling her, keep on going and calm down. And somehow all this intensity of production, I think, made you achieve something that is extremely difficult, which is this level of synthesis and subtlety, where design, making, observations of nature, testing, propositional, all these things get into a level of, I would say a higher level actually, of design achievement. And the word subtle for me is really important. In the moment you started talking about how this is being moisturized by the other side without touching, I thought that's the ultimate statement of subtlety. Because if it wouldn't be subtle, you would have a bloody ugly pipe coming from the back moisturizing, or you would wait for some rain to come from this side. But the fact that they don't touch, that the touch is actually through the material, keeping this with a level of moisture that allows the bacteria to change color, wow, that's something, isn't it? This is quite an achievement with the constraints and the complexities of the making, which should not be underestimated, because this is going for a long time in terms of how the slip casting can evolve to a level of refinement in terms of thinness, in terms of geometric complexity, the time of drying, shrinking moments, all the stuff that one almost takes for granted. You look at it and say, easy stuff, few panels hanging on the wall. Well, or in the middle of a room. Well, they take months until they achieve that level of refinement and subtlety. And then they make sense. And then they seem to be in the right shape, join even together, have no cracks. And you think, wow, so easy with all the levels of difficulty. And I take this really as a model project in that sense, because for me, it was a big learning curve not to give up and not to be over anxious of not having the right answers in the right moments. The project needed its time, and I think good projects, in particular experimental projects, they need their time. They need these questions not to be all resolved in one go, but there needs to be a belief in the project. And I think we had that. We had clearly a belief that chromatic variations, aspects of making that are quite complex to handle. At the time, there was no idea even where to make them. Then the possibility of Tony Kumela might give a help with something was sort of growing. And you really conquer the territory of the project. You conquer its innovation. You conquer its logic. And that only comes with this time. And I think this is phenomenal. I'm just greatly curious of what's going to come next. What's going to happen now. That will be seriously interesting now. But it's great stuff.
Well, usually what I do is doing recommendations about how to follow and trying to expand the potential of the project. This is basically what I'm trying to do with you. But I think in this case, it's worth it to step out a little bit and see how important it is what you have done in general as a reflection for architecture. So I'm going to talk about 3 little things that I think are super important. First, Marcus was talking about that experimental project has to avoid problem solving. And I think this is super important. real findings, real innovation, and many people is talking about that, do not happen when you are doing design as puzzles, in which you are doing like, you know the solution, you know the brief, the brief contains the solution, and then you just go for it in a, let's say, fancy way. So I think real finding is about really letting you material, clients, people, society, places, sites, techniques surprise you, and this is requiring a very special methodology in which it's very clear that you are following. For example, cross-disciplinary is the only thing that is taking you to this kind of result. You have a biologist and is playing a role. You are taking into account there is a lot of software in here, a lot of computation. So all these are ingredients of this architecture, and is not problem solving anymore. No. Second thing that I think is super important is you are somehow criticizing or let's say not making sense anymore this idea of industry becoming something that is separate from craftsmen. I think in this table we are seeing the highest level of computation together with highly craft glazing process, together with molds that are again quite craft in a way, together with processes that are industrialized in a way. So there is a transition, and this is not happening like craft, computation and industrialization in disorder, but you are bringing a mold and then you are putting it probably 3D scanning something. So this is a circle in which all these elements are connected in not a linear order again, but informing each other in a circle that is close. I think this is super important for those architects that are thinking precast is always better. It's not always better. Sometimes you need craft, and sometimes you need go into on-site construction, and usually it's always a combination of many things. And third thing that I think is super important, I'm totally fed up of architects that has been studying 6 years. In my when I was in the study, it used to be 10 years, and they don't know anything about light. They cannot mention 3 chairs that they like. I mean, who are the authors of the chairs? They don't know anything about color, and they don't know anything about textiles. And they go to what some people call real life, and they are kind of proud. They say, you know, structures are more important than colors. That's not true. For your users, colors are more important than structures. Structures, what the hell? They can disappear. They can be invisible. They can be in the inside of a wall. So as in this inversion of things, I have the theory minimal architecture is just for saving time for architects. And many times it's not making a better space for living. And it's a little bit contradictory with the real anthropological sense of people. So in here, I see all these inverse. Structure is important, but it's also important the color change. It's also important how you welcome your user, the texture, the finesse, the detail, the perception in a way. So only for these 3 issues, I think is very, very important what you have achieved. Of course, it's having a lot of potential and a lot of development. And if nobody is making nice comments on the future, I will do. But I think this is stepping out and saying, I'm not problem solving. Cross-disciplinary has been super important. I'm inverting the hierarchy of what architects consider important, because color change is the most important, and you can do it. I mean, it's very important. And craft and industry can collaborate with compute in a different way. It's super important that you have this agenda clear in your mind, I think.
I just quickly want to congratulate you. I think this is really amazing. I mean, I'm amazed by most of the stuff here, but this is just wow. The intricacy of these patterns, the material, the experiment that you connected with the industry, that you have this biological aspect. It's really impressive. I'm really impressed. And what I like most is actually that hidden irony that you criticize the synthesization of our environment, and then you create a material that is super synthetic somehow. At least it looks like super synthetic, but then it's used to facilitate the growth of algae on the backside. So I really like that kind of hidden joke that you're making, if it is supposed to be a joke. But
I just wanted to add another thing, which for a long time I have been convinced that there is something called the geometry of a program. And that is extremely difficult to find. If you have the program of a building, of a landscape, of a wall, of a set of tiles, there's something about the search for the geometry that fits into that. And that can be on a larger scale, and there can be a different geometry on a smaller scale. But to find the geometry that you feel comfortable with when you talk about the specific program, I think is brutally difficult, because it's not an imposed top-down, I want to design something that has a reaction diffusion. I want to design something that has just a set of striation lines. What is it? Why it makes sense? And it's not necessarily only a functional conversation. And I think you are clearly one of those that goes through a whole set of possibilities. And there are many more. I remember the studio was full of 3 or 4 more tables full of stuff, where the geometry gradually started making sense in its different parts of the project. And I do remember when we had a conversation where the stuff you were doing, I called a bit old-fashioned. Now, it was a very subjective comment, but sort of a bit like you're losing it. It's becoming a bit of a generic geometry exercise, which I'm not sure about. I'm not getting the relationship between these geometric studies, the morphologies, and the work you're doing. And I left. One more day, I left, and I thought, what the hell is she going to do with that? And I came back, and this started emerging. There was different studies, and the other side started emerging. Meant that, in fact, you have something like 3 or 4 different types of geometries happening at the same time in this work. You have these points. You have actually the ones where there's nothing, there's only pure topological variation. You have the much more striated, linear, ridged system on the other side, and you have something in the middle, which we can't even see, which is much more sort of pointed and creates more of a bumpy landscape. And again, it's not purely a functional, performative conversation. It is that as much as something of an intuition that you as a designer develop along the lines of saying, I need this level of density in order for having the coloration be related to it somehow. And that relates to a certain size that exists on the others. And I think others get it. That's the fascinating thing. I think the other ones, they're not even questioning anymore sort of how performative, how much bacteria is growing there. Who cares about how much bacteria is growing? Some bacteria is growing. The thing seems to have its right scale, and it's in the right place. And that can only be achieved by having this intensity of pursuit of experimentation and finding a geometry for its own program, for its own place. And if you have the time in your projects to achieve that, that's fabulous. And any other person who goes through this process knows exactly what this is. It's sort of, you've often finalized the project and said, it didn't look right. What does it mean? Maybe it was a bit not very subtle, maybe it was a bit crude, but maybe the geometry was not the right geometry for the whole project, but you insisted on it, and we all know what it means. To get that right, hugely difficult. Fantastic achievement.
No, I just want to congratulate you, Nina. I think that in a way, maybe I will summarize some things that they have been said, but in my mind, I keep on having the word cognitive. And that is because I see that there is a lot of complexity, levels of complexity in your project related with computational design, related with digital fabrication, related with biological design and understanding. And I think that each one of them by themselves, they can be nothing unless the architect or whoever, let's say, with cognitive capacities comes and take a decision. And I see multiple decisions taken in all your process. Maybe in a final piece you can never say, but I see that decisions in all the levels. I see this capacity of giving a sense to computational code, giving sense to the fabrication process, giving sense to the biological responsiveness, and this capacity of giving sense to all these things together, I think it's the most important aspect of your project, and it's also a symptom of you being very talented, and that is why I want to really congratulate you for the work.
And Nina, you were very lucky, because without Tony, we wouldn't be here. I'm saying that because to me, like, we found Tony in 1995. Before. No. 1995. We found him because one of our clients wanted to have a Gaudi park, which is the Diagonal Mar Park. And one of the things we hated the most was the trancadis, to work with the ceramic, because we just hate it. But this was exactly what Mr. Hines wanted for our park. M'entens? No, sí, no me després. So that collaboration made successful the second project, which is the market of Santa Caterina, which would be much better to do now with this project. Because one of the things we wanted to achieve by working with ceramic was not only to bring ceramic out of the bathrooms and give that dignity to a material that was in Barcelona on top of roofs and under the balconies. We wanted to bring life. But technology in those moments were not so advanced. So the only thing we have done was to make a salad in the shape of an image, because technology at that moment was Photoshop. And we were amused by the capacity to the order command pixel. And we went to Tony, that it has the same enthusiasm as we had with you, and say, sure, let's pixelize, let's serigrafiar. Claro, pero tendríem que fer la coberta una altra vegada amb aquesta peça. And so I can't stop thinking in everything that you have been doing, but especially in the experiment of Marcus, which I wanna congratulate you, because it is so necessary in school to have the students experiencing the collaboration with industry, because if you don't have Tony, this is not possible. So if you don't have Escofet, you can't deal with anything. So we have many ideas, but it seems that one of our capacities to choose the right manufacturer. And we were lucky because Tusquets told us about the fantastic cups and tea things that this man would do. And so what I see today here is almost like nostalgic for me. I'm always envying that, and I'm thinking about Enrique a lot, because for sure now he would finally make a salad of all these bacteria, even because I have to tell you, it was impossible to decide the color. Why not let bacteria decide the color according, being the effect of manifesting the cause? And so I don't know what I'm telling you, Nina, but I congratulate the partnership in between you, the YAC, the students, and Tony, because it makes me think how architecture is going through experiment as you are doing here. Because I'm insistent, ceramic in the 90s was condemned into bathrooms. And this is what I'm congratulating you for all this partnership today. And from the YAC.
Tony is a person that he, apart from the capacity of craftsman that he has, he is a very open-minded person in terms of exploring new ideas. I mean, we continuously learn from him, but he also wants to learn. I mean, like a few months ago, he installed in his installation a robotic arm, because he saw out of that work the potential of what this could do. And then we kept on learning on how we deal and understand the materiality, and how automation could be an added value but not the main goal. So this combination of automation, craftsmen and cognitive decisions is a combination of industry, academy, and architects and professionals in the world. And I think that is a great project to finish with. And it's great to have Tony here in the presentation and, of course, during the process.
Voy a expresarme en castellano, a lo mejor es más fácil, bueno, para mí seguro. Yo entiendo relativamente el proceso seguido por el problema del idioma, cómo pasamos de la bacteria al objeto, ¿no? Esto ya empecé a tener dudas cuando empecé en mis contactos con la Architectural Association y todavía no los he resuelto, pero aquí estamos, ¿no? Para mí es muy importante esta visión y esta manera de entrar en el mundo de la cerámica totalmente libre, sin límites, que nos fuerza, que fuerza al material, que nos fuerza a todos. Pero lo que más me preocupa es la parte humana, que no la técnica, que es llegar al fracaso. Es muy fácil con la cerámica no llegar a ningún resultado y a la gente joven tener un fracaso de este tipo, estamos en el límite. Yo tengo más de 60 años y he aprendido a vivir en el límite, pero gente joven no lo ha aprendido. Entonces hay que aprender a convivir con la cerámica con este límite y es lo que me hace sufrir de esta colaboración con la gente joven. Pero para mí es absolutamente enriquecedor y...
Of failing. That was one of the key success of his thinking, not being afraid of failing. And this is the advice I think that you're giving to the students.
But, you know, I was bracing myself to come here today and face a lot of failings. I was really, when I was coming in the airplane yesterday, I was thinking half of the work probably is cracked and didn't work out. But it's strong enough. It doesn't matter. It actually doesn't matter at all. It's part of the process, and it will be super interesting to see the failings and for us all to think through what could be done differently. Where is that the creative power when there is failing? So I didn't fear at all that there were the failings. That's why this morning I was even more enthusiastic because I walked in and there were lots of no failings, and I thought, shit, they have been accomplished. You wouldn't expect that the pieces are there and they're pretty perfect, and you think that's quite scary actually, because you were all sort of expecting them to be totally cracked. I mean, these are students doing work, yes, even if in an industry, the industry didn't stop for these things to happen. There was a bit of support. So I think the biggest message today is that the sophistication of the design and the production happened with a huge courage, that the failings are part of it, and it could have even be like that at the end, and it wouldn't have been a problem at all. I think the work would have been as good. Obviously, we all sort of exhilarated that we see these pieces hanging here. My goodness, how amazing! But I would say that 90% of the process through, I'm very keen that there is an achievement, and I think failings are sort of people finding excuses that this didn't work and the other thing didn't work and the other one. We know that, and that's terrible. But at some point you say, it's actually quite positive, it's really quite good. In fact, throughout the whole process, when you realize that the students are mature enough to deal with it. And I think the group of students I had this year were very mature to face failings as creative moments and not as the moments that let you down and then you don't know what to do and the project is finished. Absolutely not. The project had these constant sort of revivals, and then they moved on and became something slightly different. And that, I think, made them strong. That really, and it's a learning curve for me personally, because it's far too easy to go the safe route. Far too easy, isn't it? To have a recipe and not accept that these things happen. Okay, I think it's time to wrap it up. And I wanted to thank the critics that you came. I think it's fantastic. Again, it's a matter of generosity that you spend some hours coming from all sorts of places to sit down and just look at some work and make comments. It's not done yet, but from my part, from the students that I supervised this year, I feel super humbled because I know how stressful our lives is and how many things are going on. I just met Ichaskun a few days ago in London, and this fact that, you know, I don't know, Elena, where you came in the last 2 days, and Tony came from a business that is running full on, and means that to take these hours off to come to comment on work that people have done is just an extraordinary contribution. It's incredible. I hope that those who came as critics took something with it, with them, means that they are leaving the day thinking, oh, I saw some interesting stuff that makes me, I hope, because I like thinking like that. And when I'm invited, I like to sit down and it makes me think, and I take something with me as well. So I think this dialogue that we have, and, you know, Alex is here, etc. In fact, small moments that are of key importance. I got to know that Alex was doing something with Tony. And I looked at the work, and it was mind-blowing. It was absolutely beautiful what you were doing there with the robot. So I suggested Nina to get in touch. And as it very often happens in academia, people are very territorial. They do not allow the other ones to interfere or come into play in their territory. And the fact that Alex was open enough to say, sure, Nina should come with me, and I think somebody else even went one of the times to join in to visit your factory, meant that there was an openness to say, it's okay, we did the project, it's sort of finished, it's happening, somebody else can come and do it. And this is the sort of thing that one has to say and mention it, because it's not to take for granted, because there are too many places where people are so self-obsessed and do not give space to the other ones to develop something that we then really enjoy, actually. And I thank you for having actually sent me even a few emails to say, hey, join me and come in. I haven't actually been there. You know, I'm the jealous one, actually.
My friend.
But the fact that I knew that you were going was for me fantastic, you know, because that really happened. So thank you all for, you know, what happened this morning. Thank you. Sorry. I thought she was going to present after lunch, so that's why I sort of. Okay.
Abbiamo comprato Tony anche? No. Okay, so change of plans, because I see that people are a bit burnt out. So we do a break now, we do the lunch. Okay? Yes, and then we come back in half an hour, a very short break, moment of meditation. Lubna, I will be much nicer after lunch.
Yeah, I think when
I promise you.
Lubna, when people are hungry, they are becoming aggressive.
No, I will be more energetic after and nicer.
Okay.
Yeah. Okay, let's do the small break.
Okay, Eduard, please come. Okay, half of the jury is still in the kitchen, but I would like to start because we're a bit late. And just for starting, this afternoon session is a presentation of the Digital Matter Research Studio. The Digital Matter is a research line in the Master of 1 year, the Master of Advanced Architecture of 1 year. Although we will start that session with Lubna, that she is an alumni of Digital Matter Research Line last year, and she continued her thesis project with me as a supervisor, so I include her in that group. She's the most maybe mature in the research. But just to a very small introduction into the research. During the morning, we have been seeing the group of Marcos Cruz that they are working with the idea of bioreceptivity, the idea of responsiveness through biomaterials that they react to the environment. The Digital Matter Research Line is similar in terms of searching of responsiveness. We are questioning traditional principles of rigidity or longevity, and we are basically trying to figure out intelligent construction systems working with active materials more in global. So not just biomaterials, but materials that they are able to change their property based on a specific stimuli. And you will see a series of different kind of materials, starting with, say, memory polymers, nylon-based muscle wires, variety density in same memory foams, and some other materials around. And to say that basically our focus is to how to understand that architecture and buildings can become computers that are able to be programmed at a nanoscale of the material, and be responsive not only in the environment, but also on the user's needs. So how part of those technologies can partially empower the users to be also part of the, not so much of the design, but basically of the performance of the building. And before giving the word to Lubna, just to say that this research line is not only led by myself, but there is a great group of people. Alexander Dubor, I don't know where he is. So Alexander Dubor is an assistant on that studio the last 3 years. And Angelos Chronis has been also the computational expert, and more than that during the year into the research studio. And a lot of other external people that gave their feedback. So just to say also that especially because we are not material scientists and we have very many limitations on how we can go deeper into the material, for many years I have been searching for material scientists and experts that they can help us and support us on that. It's not easy to find a material scientist that also understands our way of thinking in terms of design and in terms of application. But I have to say that I'm extremely happy that this year, for the first year, we're collaborating with the Italian Institute of Technology. Ilker Bayer is one of the main researchers from the Smart Materials Group back in Genova. And himself, together with Athanasiou, they have been a key contributor to that work. They have been the material scientists that they were able to understand most of the things that we have been trying to achieve, and they have supported us on that. Ilker, thank you very much. Thanks also to Nasia that she didn't manage to be here. But with these small words, well, I pass the microphone to Lubna. Sorry, before that, I need to introduce my jury. So starting from the left, we have a series of different people. Edward Cabey, a director of Apparel Architectural Studio and also faculty at IAC. Elena Rocci, we have been with her during the whole morning, so no need of further presentation. Is Ascon as well. She has been with us during the morning. Marcos Cruz, Ilker Bayer, that I already presented him a while ago, our material expert. Manuel Kretzer, that he is also a stable contributor to the research lines since the very beginning, basically because he is one of the pioneers on working with smart materials. So every year we kick off the research line with a workshop with him, and he's also visiting us for feedback. Great to have you back, Manuel. And I don't know if I am forgetting something. Carlos Saez, he's also another material scientist, so we have two material scientists basically on the panel. Come in the front. Carlos has been also supporting us partially during the year. He is the mind on the material aspect as well. Jonathan Minchin, you are just in the corner and I haven't seen you. So Jonathan is the coordinator of the Green Fab Lab, expert on materials as well, biomaterials, but also the understanding of how materiality can be applied into the architectural scale, since he's an architect. So John, can you come a bit closer to the jury? Yeah, and with that would be all. I hope you enjoy the session. I hope you are not very tired, and Lubna, break a leg.
Hola. I did my thesis on evaporosity. So evaporosity is the title of my thesis, and I'm gonna explain it in a while. First, when I started to like a guideline for my thesis investigations. Of course, we all got lost and we didn't know what to do, but in the start, I was interested in soft materials. So I started to investigate what are the options or what are the choices to use soft materials, what are they, how can they be applied, and their properties, their characteristics. And at first it was very vague, like I had an idea how to create a new innovative property out of material by articulating something in it, something like either in the way structural or it is material properties. So I had like some state of art of different soft materials which are used in architectural applications or as research investigations. And then what was interested me since the start is that soft is anti-fragile, because soft materials, they don't break like glass. They can wrinkle, they can grease, they can buckle, but they don't fracture. And they are anti-fragile, and this was a very interesting property about them. If you have one fracture in a rubber, the fracture doesn't propagate as fast as you have one fracture in a glass pane. So what is stronger? Is it rubber stronger than steel, or is steel stronger than rubber? And then I did many like experiments about using silicon, cornstarch, and different stuff that I won't say now because they are relevant. But then I was interested in one main technique about Like I was interested in creating evaporative cooling technique using soft material, which is silicon. I was using silicon. And then I was investigating what were their traditional evaporative cooling techniques. And I was inspired from the human sweat to cool down their body. And what if buildings can sweat to cool down their microclimate? And is it like what's more affordable to do that or to use air conditioning? And then I was researching ancient evaporative cooling techniques, and there were pretty weird, interesting one that has a jar full of water and then a wind tunnel. So the water would evaporate in the wind tunnel and go to the house, and then it cools down. Or like in the desert, they used to get some sticks and they wet it out and put a fan. So this was the air conditioning. And another thing that interested me was the urban heat islands. How the temperature in the city is 5 degrees more than suburbs because of the facades of the buildings. It's concrete, it's flat, it absorbs more solar heat, and the buildings form a canopy of heat that prevent it to cool down during the night. And because also of the vegetation and the soil in the suburbs, which it's a water reservoir, and when the water evaporates, it cools down. Even the tree, they transpire, the plants and everything, and they help to cool down the microclimate. So how can we interfere in the city in the way the buildings are made to take this property into the city, which is 5 degrees less, basically. So as an introduction of evaporosity, cooling is one of the major concerns of building in hot climate. The problem is exacerbated by the heat gain of the roof of flat concrete facade, like I said. So the material scale of the building fabric has to be rethought in a way to stimulate direct and indirect cooling strategies, because it can be passive and it can be also controlled. Because, I mean, the perfect scenario would have everything passive, but sometimes you have to introduce some things, some kind of performance to tune the other field of passiveness, because passive can't be controlled. And then the flatness of the facade could be transformed into a porous one, similar to our biological skin, able to absorb and perspire. Evaporosity is an evaporative cooling performance, and I would stress on the performance because maybe I'm not having a perfect result, but to have a kind of performance is like a beginning of another kind of research, which can be more forward developed. A performance of porous silicon within a humidity buffering base to neutralize the thermal heat gain. So talking about porosity, if we have microscopic images of human skin or hard tissue or hard patch, they're all porous. There's nothing flat, nothing that's closed. Everything is porous. And it's interesting because this is the way it has to be, to breathe, to communicate the heat from outside to inside. And thus, I was trying, how can I create different porosity levels in silicon, which is the material I was investigating with. So I used different grains, like the beads of the necklaces, wax, salt, sugar, and like everything that I can use and take it out. So salt and sugar, I can wash it away, but beads, I have to take it one by one. But I can have different sizes of beads. And then I tried to make a catalog of porous silicon things. And then I had different porosities, and then I was trying to study the permeability and capillarity of these. And then trying to see if I put a small grain with another smaller grain in half equal amounts, how much is the capillarity? No, if I put 3/4 of bigger grain and 1/4 of a smaller grain. No, if I put them in equal amount, how that would change? If they were like packed, mixed together, or were they put like equally above each other without being mixed? And it really varies, but it's like it's a basic knowledge of the soil. Like the more small pores you have, the small grains, of course less permeable it is, but more capillary it is. And also about permeability, which also like it's common sense. The bigger the holes, the more permeable it is. And then I had a prolog, which is a catalog of porosity. And as capillarity works better with low pores, and permeability, of course, works better with bigger pores because it can hold more water. And then I had different porous textures. So these are some of them. And at the first stage, I was interested in doing this facade material that could be porous and could absorb rainwater. And then this is the passive thing, no? Because you can create the material, it will absorb right away. Then what is that that extra thing that to control the passiveness? I used inflation. Inflation was to inflate the pockets of the porous silicon to squeeze out the water, and then it would sweat out the water to cool down the microclimate. So I used inflation to squeeze the water out. And then I start studying where do I have the squeeze, or where's the force of squeeze to get more water out? Because, and why inflation? Why do I want to squeeze? Why would I just leave the pores, they absorb water, and wait for them to evaporate? No, but no, I want to tune the evaporation because there are easier ways to put aerogels or agar and let them absorb water and wait for them to evaporate. But what if I want to tune the evaporation rate? I want now it to evaporate faster than later because now I want a direct drop down in temperature. So to tune evaporation, basically water, it evaporates by itself, yes. But if the water has a certain kind of kinetic energy, it will evaporate more. So squeezing the water out, the water particles are moving, and the water is getting from the bottom pores to the outside, then evaporation will happen faster. But I had like an ideal case of stage 0, 1, 2, where 1, it's in a normal position. 0, I vacuum the pores, so no evaporation happen whatsoever. And 2, it inflates, and then evaporation happens faster, let's say. And this is like how it's inflating, normal, and vacuums. But it didn't work because it's really hard to vacuum and to get all the pores closed until the surface. It doesn't work that easily as the sketch. So then I moved on different tests. Okay, what if I have a porous pocket and I inflated like normal inflation? I have it, I inflate under it. How much water does it squeeze? First, yeah, of course it will squeeze, but no, it doesn't squeeze water at all because the water goes to the edges and they stay, they don't drip, they don't go out. What if I divided the bucket to, like, let's say 1, 2, 3, 4, 5 buckets, and then maybe inflating this way and this way, I create more force and squeeze more. But also I had better results, but still not much squeeze of water. And then what if I put the buckets inside the pore silicon itself, like it's integrated within the porosity, and when I inflate different, they will squeeze inside and drip it out. But also no, because then it will go to the bottom. Okay, then I said, what if I put the pore, what if I start, instead of using flat geometries, let's start with 3D, because maybe flat, it's always going back to the bottom. What if I do it like flat, like a belly, like inverted belly, and I inflate the bottom of it, and then it will flip out, then the water will go out. And it worked. When I had like an inverted belly, like concave shape, and the pocket was on the bottom, and when I inflated, the water dripped out like crazily, like all dripped out, and it was squeezing, and it could evaporate much faster. But also, this is not what I want. I don't want all the water to go out because I want to still have water to evaporate later. I don't want it all to go out. So what if I put the pockets on the side of this concave? So when it squeezes the water out, the water will go back to the same cave. It won't drip outside the material itself. And then I thought, well, I would have less water release, a bit less, but at least the water doesn't drip out of the pocket. So if I have facade with these small porous pockets, it will squeeze, it's inside the concave, but it will drip inside itself. And the water will go back to itself to be evaporated later when I want to. And this is the diagram of the first pocket, and while inflating, and I had like barely any squeeze of water. And then when I try to inflate different pockets, and also it's a bit better because of like different forces working together, but still no. And then like this is squeeze that I expected to work, but also no, like to squeeze inside the pockets, the material itself, but no. And then this is like, yeah, this is dripped crazily, but also no, because I will lose the water. And then this, yes, for me it was the optimal thing because it it's a lot of release of water, so it's a lot of perspiration, and the water goes back to itself. And then I made this like temperature study of like, and then I had first okay, I have this porous silicon material, fantastic, but I mean I can put it just on a facade of a building. It doesn't work that way, although it would be nice to work that way, but it doesn't. It have to be integrated with another material, like to make it more like soft is nice, but maybe it doesn't always work alone. It have to work with something else. And then to be integrated within clay, which clay is also as a humidity buffering material, and to have, like I imagine, to have an undulated clay with these porous silicon growing inside, and then the clay will hold these pores, and then it will also balance the humidity. So I did several tests, one with clay alone, and one I measured the temperature and humidity of the outside environment, and one with the clay alone, and one with the clay and the porous silicon. And the results I expected before, because when like it's like an aerogel, when you have it and it's evaporative cooling, you can reach 5 degrees less. But with tuning evaporation, you can have faster rates of evaporation with inflation. And this is my model, or my ambitious model, how I want it to look like, but it doesn't look like this. But like I imagine it like a series of clay with these undulation to let the water flow through it, and then the water will go through these pores inside these pockets that are porous, and then inflation can happen to tune the evaporation rate. And I had to cast, the best thing to cast silicon was 3D printing, because you can have smooth plastic, but it will take forever. So I have to cast foam, but you have to carve it out instead. And this, which one? This like 20 centimeters pocket, or 15. And this is like a zoom in into the pockets, the porous pockets. And this is the digital model with how I imagine the clay and the silicon being integrated with them. And they will act on cooling the microclimate. And this is a section of the pockets with the porous silicon, and when it inflates, it drips the water out. And this is form finding, different form findings to like about It's not as it looks in the ambitious physical model, but it's okay. Okay, so it looks like that. It was supposed to look nicer, but it doesn't. Okay. And these are the pockets, that the one in the video, that one that inflates, this one with the pocket inside the silicon. This is single inflation, multiple inflation, and button inflation. There's some series, and this is like the catalog of, and this is the catalog of the porous silicon. And they're all done with these are done with beads and salts and sugars, and these are salt. So I put the salt, and when and I pour the silicon. When the silicon cures, I wash the salt away, and I have the porosity. But these are bigger. These are with wax.
So you have a gradient control of the porosity of the silicon along this kind of form, right? Okay, wait a minute. You want me to start, or Marcos?
No, you go ahead. I do. No, thanks for the presentation. I think the film that you showed at the end, for me, was very important, actually, because it showed really how this worked. And when we look at the small prototypes, we obviously are super interested in understanding how they're made. But I think in the film, the level of abstraction they have, that you're zooming in, gives us really a sense of quality of what it could do. I think it was haptic, performative. It had the right scale as well, because you had the feeling that you were zooming in almost as if you zooming in into the skin, human skin. So that I felt was really important part of the work. What I think is really intriguing and interesting at the same time is the triggering effect of the inflation, because that's sort of the grand question of, you have an effect that you want to achieve, but you need something to cause the effect. Now, is what causes the effect just a, by the way, is that it could be something else? Or is it a quintessential part of the whole process? And what causes then the inflation? Means, what causes the inflation in order to cause the squeezing out of the liquid that then evaporates? So it required several steps. And I actually like the different steps. I don't see that as a problem, but because you showed some architectural possible applications, even though they must have been rushed, and I'm not so sure about the tower, to be honest, but on a smaller scale, I think it brings it back, and it's interesting that we're in front of this wall, to the discussion that we had when Elena was asking Jessica about the behind, what is in the back. And I think the same issue applies in a way to your work. What is behind it? And no coincidence that Areti immediately lifted this up and made us see the behind, because there is really a big question about the front and the behind having different operations. And in our skin, we have that. Our skin is not only the front, it's actually the back that triggers what happens on the front. So there is an interfacial condition of what triggers what then has an effect on the front that would be interesting to take further, to question further, what is this back condition? What makes it happen? At some point, I was imagining even that people could trigger it with their own movement, or by squeezing against a rubbery wall system. I mean, I personally have spent quite a few years of my life thinking about what could be walls that are flexible and pliable and movable, because I love the idea to actually be immersed in them. You know, some people made very interesting psychological interpretations of why I like doing that, but I found it absolutely fascinating because for the sheer fact that everything around us is simply hard, and the dialogue with a flexible skin, I still think is hugely fascinating, but it needs that engagement. And I think the work, again, is a seed for something. I see, as all the work that we saw in the morning, they're great steps for something to happen with it, because it hasn't been done, it hasn't been achieved. And I think the material studies are super rich, but you have a bit of question of the back, sort of, how's the back triggering this? Are we the ones, is it a piece of inflation that happens because of the environment? Is it a censored system? What is it? And it needs a bit that completion to the story for this to happen. And then I just finish by also asking the size of this. Currently, they're sort of spots. They're like as if they're small pimples on a skin. Now, is it the entire skin, or is it a set of exceptions? And I prefer thinking it as a much more variable skin rather than the exception. Currently, there seem to be exceptions. Now, what makes the difference if they are not spots as an exception, but they are much more of a continuous changing landscape? And in other words, instead of you saying that I have 4 or 5 different types and I need to choose one, why are not these 4 or 5 actually integrated in a seamless situation? Because we know that our skin, just take this one here, is very different from this type of skin or from the other one. And they are continuous. They are not saying, I'm better than you. They're just in different places. And I would imagine your architecture to having this sort of continuum. But great.
I also like the work a lot, but I will make some comments about the material science because of my background. I was going back to the skin. I think I was thinking maybe more it could be something, because skin is a multi-layer from what I know, a structure. So instead of having this pushing action or like squeezing the sponge type of action, because I think it is architecturally not very, let's say, doable. So maybe the process could be more like how the skin really works. I mean, it could be a design towards going in that direction, like some kind of triggering because of some kind of temperature difference. That a material can be in the multi-layer structure. One material can be more sensitive, can cool with a different thermal conductivity, for instance, like our skin does. So to me, all the other thing, like all the other the concepts were really interesting, but to me the squeezing action was a little bit, let's say, it looked like an if you want to associate it biomimicking, it looked like an animal, you know, like an animal is making a move, or a living organism, whereas, you know, the skin just does it in a, I mean, we don't see our skin moving when we sweat, basically, in large proportions. So this is
material system, but I am actually glad that you didn't, because then it allows us to open up our imagination of thinking that this actuation could possibly happen in a different way. So I wouldn't like to see pipes and pumps integrated into that, but I would like to think as a next step of it, a kind of an actuation that it is inherent in the properties of the system itself. And the fact, I think that another interesting aspect is to work with this variety of porosity within the surface, because it allows us to start thinking of surface totally anisotropic, no? And would be great to understand in a more clear way how the porosity is being placed based on whether it is a sunny, not only the depth of those pumps, but also the density of this sponginess and this porosity of the material based on orientation or based on the form.
I really like your the concept, the idea of the building as an organism that is able to sweat and that that does something rather than just a static building. I would be curious to see some speculations on how this really looks and how this not only works technically but also how this affects the people who are inside the building. Like, when does it sweat? Does it sweat a lot when there's a lot of people, when there's exercise? And does it start to smell? If it sweats too much, do people have to leave the building because the building just doesn't stop sweating? Things like this. And also, I'm not sure about the material, the silicon. I mean, it's a very expensive material. It's very unsustainable. So I don't know if that's the right choice, but I think you also explored different types of materials. So there must be a reason. Yeah. Yeah, I'm just not sure on a larger scale if it works on a big scale. And also, I mean, Marcus would probably like this, but what happens if it does sweat a lot and if there's actually mold growing or bacteria or algae? Yeah, is that something that you want, or? Okay. But if the water doesn't evaporate, it will go somewhere, and maybe there will be stuff growing. I don't know if that's something you would like to happen, or if that's something you would try to avoid. These are things that you could work out in scenarios and really think about possible situations.
Thank you. I was interested by understanding the scale and to see how the anti-fragile things was going to grow. And I think I wanted to ask you if in part of the process you were thinking to grow the thing as the skin is growing when we get older, for example. When I see the building, it seems to me that you blow up the porous, while I think it would have been interesting to see how a skin, it would have been interesting in order even to understand materials, another question, to see how you could grow from that thing a kind of material. Actually, the best model now, to me, it's this, which is not a model, right? For you, this is to exhibit, probably. But it's very interesting here when we see a grid and you fill it with the material, and probably this can be a system to grow a building. The other one is very specific. So I think as an architect, it would be interesting once we experiment with the material to understand the possibility there are in there the material for building and growing new organisms. And probably, I mean, if you keep going working on this object, probably, for example, if we keep these as a square module, what it would be a way to start to assemble all of them. And in the moment that we are always subject to gravity and the buildings, they all fall apart, what it would happen to the skin. And that, to me, it's interesting because we get bigger and our skin decay. But it has an amazing capacity. The older skin, it's on top. And the younger skin is down below. And so by working in terms of biomimicry, learning from nature, it would be interesting to start, and I think you should do it, to start to see how this, it's interesting to start to question your object by increasing the scale, because in architecture, this is what we do. We start with a little model, and until, you know, we go out in reality and we see not the dimensions of our beams, but the weight of it. And so a pillar starts to appear. So there, I think I would have dedicated a little bit more of time for questioning the project by increasing the scale, and it seems to me that you did it at the end. But I think that what I really appreciate in your presentation was this obsessive what if, what if, and what if, and what if, and what if. And so it was amazing. And now I would like to tell you, and what if? And I think that's your capacity, and you should keep it. Because very little time we found people that are able to say, oh, this is an open project. So be a what if, because it will bring you very far. Thank you.
I have some suggestions trying to increase like the potentials of the research that you have done that is very valuable. My first comment is I think it would be interesting to make a distinction between porosity in terms of fabrication and porosity in terms of performance. Materials that are usually including porosity in their fabrication, for example, Eton is a brand for radiated concrete. What they do is they insert air in the curation of the concrete. Is a very cheap material. I'm using it instead of bricks or some other things because it's environmentally better. But at the start, what they included the air in the concrete was because of the fabrication limits, weight, price of the material, density. So they have created a concrete that you can cut with a knife. But then the best performance is acoustic. It's a material that is very good in terms of isolation. But then the type of procedures that you have to follow, if you pay attention to and you try to optimize the acoustics, is different. So I think in here there is a bit of a mix between why I use porosity while I'm fabricating and how I could use porosity for a performance that is ventilation or breath. And I think a further step would be distinguishing what is simply making me easier to fabricate and what is performing better. I think that would be interesting to see the applied material. My second comment is when you contextualize the design in the shape of a tower, I think it will be quite interesting also to enjoy a little bit the different levels or scales of porosity. Like you have the material, but you can also have courtyards, you can also have windows, cross ventilation. All these elements, you have to understand what you gain, for example, from planting around a building, from positioning your building in a hill, so that you have the material porosity, the porosity of the typology, and the porosity of the landscape. I think it's very important that when you make this exercise of contextualizing, you don't lose the complexity of the different achievements you can do with your hypothesis. And a third suggestion or comment is I think when you see a wall, most of the facades that we have been seeing during the day have been a bit like, let's say, isotropic in the way there was no distinction between window, wall, entrance, cover, bottom part, ground, and in a building all these distinctions are super important. The scheme is not the same when you are in the bottom, in the ground, touching the ground, when you are on top, when it's a window. And many things like, for example, views, have to be revisited, like how views are working when you are doing a facade like this. Obviously, price, but many others. I think all this diversity, see this small facade. I mean, you have 5 or 7 different situations, and it's because of something. This is light without view. This is entrance, light, and view. This is again light without any view. So all this is because of something, and I think we are all aiming you to open a little bit more the system so that the variety of the solutions are more, and also for me it will be the functionality of the applications. It will be wider if you open a little bit the versions.
I think it's not easy to comment on your presentation, and I think it's sometimes I was wondering when you were presenting how much you believe in what you're proposing, how much you believe that your research is really come to a point that you're proud of, and I think that's very strange because I think that there are many
very, very interesting moments in your work. And Marcos mentioned the video, which you show at the end as a kind of last piece, which is not anymore at that moment part of your argumentation. You've already explained your project as if you were a scientist, which you are not. And then afterwards, there is a kind of result, which is for us to see. And it's terribly exciting. And what I was struck by in the video is that the video it's something that talks about your research, about the material investigation that you've been doing, but about so many other things. No, it engages many things. It creates a reaction. I mean, first of all, it works as a cinema. No, we were suddenly spectators in a movie theater, looking at something that I think we were all somehow disturbed by, and we were looking at something we hadn't seen on the screen before. It was pretty. It was somehow disgusting. It was weird. No, I think many adjectives somehow came to mind, and I think that you have to look at these. You have to look at what are the potentials, and then the, let's say, technical one, because I think your presentation is really technical. But that video suddenly talks about construction, it talks about the building industry, it talks about effects, it talks about perception, it talks about systems of construction. I think then eventually it starts also really to talk about space. And I think this is maybe something that you don't take advantage enough. When I look at the prototype that you do with ceramic for me is when you move to a kind of composite assembly, maybe it's the part that I somehow relate to least, because I think that there's a really high contrast. Besides the fact that they have a similar form, that they are both curved, actually, in terms of how they function as materials, they're very different. So I would question that. But I was wondering, and I think maybe one of the reasons why it's a little bit now difficult to understand what's the next step of this research, or is this a project that has a future, or is this a project that now somehow we close? Is I think the fact that maybe you don't relate it enough to the real world. All of what we see on the both on the screen and also here is it's new somehow, and that's the criticism that I have towards the ceramic prototype. I was wondering whether, rather than implementing it within this, to what extent you could use this really to target existing buildings. No, existing buildings have problems when it comes to humidity, when it comes to ventilation, when it comes to climatic performance, all buildings, and they need to be reworked. And I think that this has a lot of potential to start to be inserted within cracks of this place, no, for example. And I think that if you start to see your project in those terms of saying that this actually can be implemented tomorrow. I'm not an expert in silicon, so in terms of when it comes to really technicalities of whether the silicon is a viable product, this is something is difficult for me to understand. But at least if you think of kind of common problems that we have as architects and as people that are involved within the building industry, I think that there's an immediate future to this, and I think you're very close to having something that can be embedded within, let's say, retrofitting projects. No, so I think don't forget in this kind of project that are really in which you really go deep into a topic, sometimes to step out, to reflect, and to start to really kind of dream. And video is good for that, on all the potential that such a piece of work can have.
I can just add a few more comments to this. It's always difficult at the end of a string of comments to add, but there is one thing that for me also very much brought out through your video was the direct relation between when we see the comparison of human skin, and we know as humans that we're very good sweaters. You know, we're professional sweaters. There's in the mammalian kingdom, the reason why we don't have hair is because we're so good at sweating. So for me to see a direct comparison between human pores opening and then also the synthetic pores opening, and actually wondering which one was which at certain points, I found that actually to be quite a successful accomplishment in artisanry. when we talk about the relation to business, or not to business, we say industry. When we're looking at that, this has application. This really does have something that can be used. And if we are taking an example of something which is so successful anyway, and saying a direct resemblance to that, I think this has application. But that's come through your absolute dogged pursuit of this application's success. There's been a tremendous amount of trial and error, and really deeply experimenting into making that work. And I've seen some of that process go through. So just to end on that artisanry and the sort of inventor spirit that you've embodied, congratulations on that.
I will just close by saying, especially following a bit what Elena was saying, that Lubna has been a student that almost every 2 weeks she was coming with another what if, because also the process has been changing and influencing that development. But one thing that she was very consistent on from the very beginning was the contribution of soft materials for the performance of cooling down the buildings. And I think that all the previous experiments that you haven't been showing with the different materials and the different additives and everything has been really focused on that performance. And in that sense, I think that this is successful. What it comes and should come next in how this is becoming more integrated into, let's say, the design or into a more specific application. When you're showing a tower, everybody expects to have something very much finished, no? And I think that it's a challenge, and you can really push forward for that. But yeah, thank you.